Among the strangest objects in the universe are neutron stars, collapsed stellar cores packed so tightly that a teaspoon of their material would outweigh mountains. Inside them, matter is crushed beyond anything that can be recreated on Earth, and physicists still debate what truly exists in those hidden depths. Today, we explore the mysteries locked within these ultra-dense stars, from exotic particles to possible oceans of quarks. If you enjoy journeys into extreme astrophysics, please like, subscribe and share, and tell us in the comments, what is your biggest question about the inside of a neutron star? Thank you for watching. Now let's begin. Across the Milky Way, neutron stars are scattered through the galaxy in a pattern that reflects the lives and deaths of massive stars. They are compact stellar remnants, but in this first view, they are treated simply as points on a galactic map, each one marking a place where a massive star once ended. Their positions are not random. They are most common along the thin disk of the Milky Way, where gas and dust collect and where star formation is most active. In this flattened region, which includes the spiral arms, clouds of cold molecular gas give birth to massive stars, and after short lives, those stars leave behind neutron stars that still roughly trace the same broad structures. The distribution of neutron stars therefore follows the spiral pattern of the galaxy, even though the individual objects can be difficult to see. Astronomers infer this pattern by counting different kinds of observable neutron stars such as pulsars and X-ray sources, and by comparing those counts with models of how many massive stars once formed in different parts of the galaxy. The picture that emerges is of a dense population concentrated toward the inner disk and along the spiral arms, with fewer neutron stars at large distances above or below the galactic plane. Near the center of the Milky Way, the density of stars increases, and so does the number of neutron star remnants expected to exist there. The inner regions contain old and young stellar populations mixed together, and many generations of massive stars have already lived and ended. This history implies that the central parts of the galactic disk should hold a particularly rich collection of neutron stars, some in binary systems, some isolated, some moving rapidly after receiving a strong kick in a supernova explosion. Direct observation in this region is difficult because thick clouds of dust block visible light, but high-energy observations in X-rays and gamma rays reveal many compact objects that fit the expected pattern. This central concentration blends smoothly into the broader disk population, forming a gradient where neutron star density increases steadily toward the galactic center, just as the overall stellar density does. The resulting map is not sharply defined, but it shows clearly that neutron stars belong primarily to the main stellar body of the galaxy, rather than to its faint outer halo. Along the spiral arms, young star-forming regions leave further imprints on the neutron star distribution. Massive stars live only for a short time in cosmic terms, so their remnants do not drift far from their birthplaces before they appear as neutron stars. In spiral arms, where gas clouds are still forming new stars, there are often also supernova remnants and young neutron stars found nearby. Observed pulsars with relatively high surface temperatures and strong magnetic fields that still resemble their initial values are more common in these regions, matching the expectation that they are recently formed. Over time, as neutron stars age cool and slow their rotation, many become harder to detect, so the observed population is always shaped by selection effects. Even so, when those effects are taken into account, the reconstructed distribution still follows the same basic pattern, set by star formation in the spiral arms and inner disk. In addition to the thin disk, the Milky Way contains globular clusters, which are dense, roughly spherical collections of old stars in the galactic halo. Some of these clusters host unusually high numbers of neutron stars relative to their total mass. In these environments, stars move close to one another and interact gravitationally over long periods. binary systems form, break apart, and exchange partners in a slow dynamical process. Neutron stars that would otherwise have been ejected can be retained or captured into new systems. As a result, certain globular clusters show many millisecond pulsars which are old neutron stars that have been spun up through long-term accretion from companions. Although globular clusters contain only a small fraction of the total stellar mass of the galaxy, they contribute a distinctive component to the overall neutron star population, highlighting how environment influences the long-term fate of these compact remnants. The vertical distribution of neutron stars above and below the galactic plane reflects both their birthplaces and their subsequent motion. Massive stars form close to the plane where gas is concentrated, so newborn neutron stars also start there. However, during the core collapse that forms a neutron star, the asymmetric ejection of material can impart a strong kick to the remnant. This kick sends the neutron star moving through the galaxy at high speed in a direction that is not always aligned with the plane. Over millions of years, some neutron stars travel far above or below the disk, forming a thickened population with a larger scale height than the gas from which they were born. The highest velocity objects can escape the galaxy entirely and become intergalactic wanderers, although these are difficult to trace. For the majority that remain bound, their orbits carry them on elongated paths that slowly blur the original connection between a given neutron star and the specific spiral arm or star-forming region in which it was created. Even so, the ensemble of orbits still preserves the broad pattern of a disk-aligned population. Because neutron stars are small and faint in most wavelengths, the map of their galactic distribution is built in directly. Different observational methods reveal different subsets of the full population. Radio surveys detect pulsars whose beams happen to sweep across Earth and whose signals can travel through interstellar space with manageable scattering and absorption. X-ray and gamma-ray telescopes find neutron stars that are especially hot, strongly magnetized or actively accreting matter. Searches for subtle timing effects in binary companions reveal additional neutron stars through their gravitational influence. Each method is biased in its own way, and each probes different regions of the galaxy more or less effectively. Astronomers combine these partial maps with detailed models of stellar evolution, supernova rates, and galactic structure to estimate the total number and distribution of neutron stars, including many that remain invisible to current instruments. The result is a statistical portrait rather than a complete census. Within this portrait, the Milky Way appears as a dynamic system in which neutron stars act as long-lived traces of past star formation. Regions that once produced many massive stars now contain corresponding concentrations of compact remnants, even if the original luminous stars are gone. Differences in neutron star density between inner and outer disk, between spiral arms and interarm regions, and between disk and halo all carry information about how the galaxy has formed and evolved over time. When researchers compare the Milky Way with external galaxies that can be viewed in different orientations, they find consistent patterns. Star-forming disks tend to host most neutron stars, while more diffuse stellar halos contribute relatively few. This agreement supports the view that neutron stars are a natural and expected part of the life cycle of massive stars in spiral and irregular galaxies. In this first view, the focus remains on neutron stars as markers within a large-scale structure, rather than on their internal workings or detailed behavior. They sit within the Milky Way as one component of a much larger stellar community, sharing the galactic disk with ordinary stars, white dwarfs, black holes, star-forming clouds and clusters. Their spatial distribution links them to regions where gas is dense and star formation has been vigorous in the past. Their presence in globular clusters and the halo shows how different environments can alter the way compact remnants are retained or lost. Taken together, these patterns define the outer context for any deeper study of neutron stars anchoring them within the Milky Way. and linking them to the broader history of massive stars in the galaxy. In the same galactic disk that hosts the broad population of neutron stars, there are regions where new massive stars are forming today, and where future neutron stars will later appear. These star-forming regions are concentrations of cold gas and dust, often called molecular clouds, where gravity slowly gathers material into denser clumps. Inside these clouds, smaller knots of gas collapse further to form new stars in groups rather than in isolation. Among the many low-mass stars that form a smaller fraction, are very massive, bright and short-lived. It is these massive stars that end their lives as core-collapse supernovae and leave neutron stars behind, so the present-day pattern of star formation sets the stage for the future map of neutron stars in the Milky Way. Observations across radio, infrared and visible wavelengths reveal how these birthplaces are distributed. In radio and millimeter light, astronomers trace cold molecular gas that marks the raw material for star formation. In infrared light, they find embedded young stars still wrapped in dust. In visible light, where the dust is thinner, they see glowing regions of ionized hydrogen gas that form around luminous young stars that emit many high-energy photons. Together, these traces outline spiral arms and other structures where gas is dense enough for collapse. Within them, massive stars form in loose associations and tight clusters, often arranged along filaments of gas that show how material has been compressed by gravity turbulence and previous generations of stellar feedback. In many cases, the most massive stars form in the centers of rich clusters. These clusters can contain thousands of stars bound together by their mutual gravity. The most massive members of such groups are destined to become neutron stars or black holes depending on their birth mass and the details of their evolution. Because massive stars evolve rapidly, a cluster that is only a few tens of millions of years old can already host supernova remnants and young neutron stars while still forming new stars in surrounding gas. In this way, a single star-forming complex shows multiple stages of the life cycle at once, from cold gas to bright young stars to compact remnants. The initial distribution of stellar masses in a new population, sometimes called the initial mass function, strongly influences how many neutron stars eventually arise from a given amount of gas. This distribution favors low-mass stars which are long-lived and do not end as neutron stars, but it still produces a steady minority of high-mass stars. Even though massive stars are rare compared with Sun-like stars, each one carries enough mass to significantly affect its surroundings and to produce a compact remnant when it ends. In the most active regions of the Milky Way, such as the inner spiral arms and the central molecular zone near the galactic center, conditions favor high star formation rates, so even a small fraction of massive stars yields many neutron stars over time. This connection means that when astronomers map present-day star formation in the galaxy, they are also indirectly mapping the future birth sites of neutron stars that have not yet formed. Individual massive stars in these regions go through a sequence of internal changes as they age, but at this stage the focus remains on their role as members of a forming population. They heat and ionize nearby gas-carved cavities in the surrounding clouds with their radiation and stellar winds, and enrich the interstellar medium with heavier elements when some of them explode. These processes do not yet involve neutron stars, but they set the conditions in which neutron star progenitors are born and evolve. Over many millions of years, repeated cycles of star formation and feedback shape the structure of spiral arms, building up chains of clusters and associations where generations of massive stars appear and disappear. The local environments of future neutron stars are therefore not uniform. Some progenitor stars form in dense gravitationally bound clusters where many close encounters and binary interactions occur. Others form in looser associations that disperse more quickly and allow their members to drift apart. In dense clusters, interactions between stars exchange partners and change binary orbits, helping to create systems where massive stars have close companions. These companions later interact with the compact remnants, producing neutron stars in X-ray binaries or recycled pulsar systems. In more diffuse regions, massive stars often evolve largely in isolation, leaving behind solitary neutron stars that move through the general field population. The metallicity of the gas, a term that describes how many elements heavier than helium are present, also varies across the galaxy and affects massive star evolution. Regions with higher metallicity tend to produce stronger stellar winds, which remove mass from the outer layers of massive stars before they collapse. This influences whether a given star ends as a neutron star or collapses directly into a black hole, and it affects the mass of the neutron star that forms. Observations show that the inner parts of the Milky Way generally have higher metallicity than the outer disk, reflecting a longer history of star formation and enrichment. As a result, the mix of progenitor masses and wind strengths, and therefore the types of remnants, changes gradually with galactic radius. Star-forming rings and bars within some galaxies also channel gas into specific regions, and in the Milky Way there is evidence that gas flows along the central bar into the inner disk. This concentration of gas supports high rates of star formation, and over time a high rate of neutron star production. Within giant molecular clouds, the formation of massive stars often proceeds in bursts. Once a critical density is reached in some region of the cloud, rapid collapse produces a cluster of young stars. The massive members emit intense radiation and drive strong outflows that compress some parts of the remaining gas while dispersing other parts. This feedback triggers further episodes of star formation nearby while cutting off accretion in some directions. The timing and geometry of these effects determine exactly where subsequent generations of massive stars appear and where future compact remnants later reside. Because these processes are complex and involve gas dynamics, radiation, and gravity, they are often studied through numerical simulations that are compared with observations of real star-forming regions. In external galaxies, high-resolution imaging allows astronomers to see massive star-forming complexes spread along spiral arms, sometimes arranged in patterns linked to density waves in the rotating disk. In the Milky Way, the vantage point from inside the disk complicates the view, but large surveys in radio and infrared wavelengths reveal similar complexes in the local galaxy. By combining distance measurements, gas velocities, and star counts, researchers reconstruct three-dimensional maps of where the largest molecular clouds, young clusters, and luminous massive stars are located. These maps serve as a present-day snapshot of the places where future neutron stars will be born. The time delay between the formation of a massive star and its collapse to a neutron star is relatively short in cosmic terms, so the current distribution of massive star birthplaces is closely linked to the emerging distribution of young neutron stars. In this way, star-forming regions act as a bridge between the cold gas of the interstellar medium and the later population of compact remnants that mark past episodes of high-mass star formation. In the regions where gas has already formed massive stars, each of these stars quietly changes inside long before it approaches the stage where a compact remnant will appear. A massive star begins its life by fusing hydrogen into helium in its core. Fusion is a process in which lighter atomic nuclei combine to form heavier ones, releasing energy that supports the star against its own gravity. During this first and longest phase, the core is very hot and dense, and the outward flow of energy keeps the outer layers extended and bright. The star can be many times more massive than the Sun, so its gravity is strong, but the pressure from fusion is strong enough to balance it. Inside, there is often a central region where hot gas moves in large rising and sinking motions, a pattern known as convection, surrounded by layers where energy moves mainly by radiation. This internal structure affects how fresh hydrogen is mixed into the core and how long the star can maintain hydrogen fusion. As hydrogen in the core is gradually converted into helium, the core slowly contracts and heats. When the supply of hydrogen in the very center is nearly exhausted, the star adjusts. The core shrinks further, the temperature rises, and a shell of hydrogen around the core begins to fuse while the core itself prepares for the next stage. The outer layers of the star can respond by expanding and cooling, turning the star into a bright supergiant. In this phase, the star may appear cooler at its surface even while its total power output remains high or increases. The change in radius and temperature alters the way the star interacts with surrounding gas and with any companion it might have. Inside the contracting core, once the temperature becomes high enough, helium nuclei begin to fuse into heavier elements such as carbon and oxygen. This helium fusion phase is shorter than the hydrogen phase. It produces a new core made mostly of carbon and oxygen, while helium burns in a shell around it, and hydrogen burns in a still more distant shell. The star now has a layered structure with different kinds of fusion happening at different depths. Each new layer adds weight to the inner regions, so the core continues to contract and heat as it gains mass. The balance between gravity and pressure remains, but it is maintained in a more compressed configuration. As time passes, the cycle continues. When helium in the core is used up, carbon can ignite under the right conditions, fusing into heavier elements such as neon magnesium and sodium. Later, neon oxygen and silicon fusion can follow, each operating at higher temperatures and densities, and each stage lasting for a shorter period than the one before. In the most massive stars that will leave neutron stars, these advanced burning stages proceed in rapid succession compared with the earlier hydrogen and helium phases. Eventually the core acquires an onion-like arrangement of shells, where hydrogen burns in the outermost active region, helium burns below, but followed by shells of carbon neon oxygen and silicon burning all surrounding an inner core of iron group elements that is no longer able to release net energy through fusion. The iron-rich core is special because fusing iron into heavier elements or breaking it into lighter ones does not provide extra energy to support the star. At this point, the core is held up mainly by the pressure of very dense degenerate electrons, a state in which the electrons are packed so closely that quantum effects dominate their behavior. As the core mass grows, this electron pressure can only support a finite amount of weight. Neutrinos, which are very light particles produced in great numbers in the hot dense star, also carry energy away, cooling the core and allowing it to contract further. Over time, as silicon burning produces more iron group material in shells around the center, the mass of the inner core approaches a threshold beyond which collapse becomes unavoidable. While these internal changes proceed, the outer layers of the star respond in ways that depend on its mass rotation and composition. Stellar winds carry material away from the surface, especially in stars with strong radiation pressure and high metallicity. These winds can remove a significant fraction of the star's initial mass over its lifetime. In some cases, the outer hydrogen-rich envelope is stripped away, leaving a hot compact star with a helium-rich or heavier element surface, often classed as a Wolf-Rayet star. The loss of the envelope changes how the star will interact with any companion and affects the mass and structure of the future core. In a binary system, mass transfer between the stars can further reshape both partners. A massive star that donates or receives material may spin fast to change its surface composition and alter the timing of its later evolution. All of these processes influence whether the final collapse produces a neutron star or a black hole, and what the properties of that remnant will be. But at this stage, the key feature is that the core is steadily moving toward a more compact, heavier state. Rotation and internal magnetic fields also play important roles in massive progenitor stars. A star that begins life with significant rotation can redistribute angular momentum between its core and envelope through various instabilities and magnetic torques. Over millions of years, some stars maintain rapidly rotating cores while others slow down. Internal magnetic fields generated or amplified by motions in the hot plasma can couple different layers and change how angular momentum and chemical elements are mixed. These factors affect how much spin and magnetic energy are stored in the inner regions by the time the core becomes iron-rich and close to collapse. A more rapidly rotating core can lead to different outcomes during and after collapse than a slowly rotating one, while strong magnetic fields alter the way energy is transported and perhaps the structure of the later compact object. Observationally, astronomers see massive progenitor stars in a range of stages that match these theoretical steps. Blue supergiants, red supergiants, and stripped helium stars all represent different points in the sequence of core burning and envelope response. Their spectra reveal surface temperatures, chemical abundances, and wind properties that support the picture of nested fusion shells and mass loss. In some nearby galaxies where individual massive stars can be resolved, researchers have identified likely progenitors of core collapse events before they explode, often finding red supergiants or more compact luminous stars. These observations confirm that neutron star-forming supernovae arise from a subset of massive stars that have built heavy cores and in many cases have already shed significant mass. Despite this progress, details of the internal mixing, the exact role of rotation, and the influence of magnetic fields remain areas of active research. Different models can predict slightly different core masses, envelope structures, and distributions of angular momentum at the onset of collapse. These differences matter because they set the initial conditions for the later stages when a neutron-rich compact core will form. Even so, there is broad agreement that a massive star destined to leave a neutron star follows a path in which successive fusion stages build up an inner core of iron group elements, supported mainly by electron pressure, surrounded by multiple burning shells with outer layers shaped by winds, binary interaction, and previous feedback on the surrounding medium. In this way, the structure of the future neutron star is prepared in quiet stages, deep inside an apparently steady, luminous star long before the rapid events that will end the life of the progenitor and reveal the compact remnant. As the core of a massive star approaches the point where it can no longer support its own weight, the quiet internal evolution described earlier gives way to a rapid and violent change that happens deep inside, while the outer layers at first remain largely unaware. The inner region is now composed mainly of iron group nuclei and is held up by the pressure of very dense electrons. As more material produced by silicon burning in surrounding shells piles onto this core, its mass creeps toward a limit beyond which electron pressure alone cannot hold it against gravity. When that limit is crossed, the inner core begins to collapse. In this phase, gravity pulls the matter inward so quickly that it no longer has time to adjust gradually. The collapse proceeds at a significant fraction of the local sound speed, and the density rises by many orders of magnitude in a short time. As the core contracts, electrons are forced into atomic nuclei where they combine with protons to form neutrons and neutrinos. This process, known as electron capture, removes electrons that had been supporting the core and converts charged particles into neutral ones, further reducing the pressure that can resist gravity. At the same time, high-energy photons in the hot, dense environment can break apart heavy nuclei into lighter components, a process called photodisintegration. Both effects rob the core of internal support and absorb energy, accelerating the collapse. Neutrinos produced in large numbers during electron capture and other reactions stream out of the core, at first carrying energy away. Deeper inside, as density climbs toward nuclear values, the mean free path of neutrinos shortens and they begin to scatter many times before escaping, becoming temporarily trapped in the inner regions. The collapsing core can then be divided into an inner part that falls almost in unison and an outer part that continues to infall more freely. The inner core contracts until its density approaches that found in atomic nuclei, where the strong nuclear force between neutrons and protons becomes very stiff. At this point, further compression encounters a much stronger resistance. The inner core halts and then rebounds slightly, sending a pressure wave outward into the overlying and falling material. This pressure wave steepens into a shock front, a thin region where falling matter is suddenly decelerated, heated, and compressed. The formation of this shock is a central feature of a core collapse supernova. Initially, the shock moves outward, pushing against the material still cascading inward from the outer core and inner mantle of the star. However, as it advances, the shock loses energy. Part of this loss comes from the need to dissociate heavy nuclei into individual nucleons, as the shock passes through them, a process that consumes energy. Additional energy is radiated away in the form of neutrinos from the hot post-shock material. These losses can cause the shock to stall at a radius that is still deep within the star, where it becomes an accretion shock, through which infalling material continues to flow inward onto the newly formed central object. Without some further energy input, the shock remains stalled, and the outer layers continue to fall inward, preventing a successful explosion. The leading explanation for how the shock is revived involves neutrino heating and fluid motions in the region just behind the stalled front. The dense, newly born, neutron-rich core, often called a proto-neutron star, radiates an enormous flux of neutrinos of all flavors as it cools and adjusts to its compact state. Some fraction of these neutrinos is absorbed in the layer between the core and the shock. This absorption deposits energy into the matter there, heating it and driving convection, in which hot material rises and cooler material sinks. These motions, together with other instabilities in the flow, increase the efficiency with which neutrino energy is transferred to the gas. When conditions are favorable, this extra energy pushes the stalled shock outward, again turning it into a runaway blast wave that propagates through the star. In some models, rotation and magnetic fields in the collapsing core play an additional role, especially in the most energetic explosions. Rapid rotation can cause the core to flatten slightly, and can channel matter and energy along the rotation axis. Strong magnetic fields amplified during collapse can tap rotational energy and contribute to driving jets or asymmetric outflows. The relative importance of these effects compared with neutrino heating depends on the initial spin and magnetic field of the progenitor. For many core collapse events that produce ordinary neutron stars, neutrino heating, combined with turbulent motions behind the shock, appears sufficient in simulations to generate successful explosions with energies consistent with observations. Even so, the details of the explosion mechanism remain an active area of research, because small differences in the physics can lead to different outcomes for the explosion energy, the remnant mass, and the amount of material that falls back onto the compact core. Once the shock is revived, it races outward through the overlying layers of the star. As it moves, it heats and accelerates the gas, unbinding it from the gravitational pull of the inner core. Nuclear reactions in the shock-heated material can synthesize new elements, including some of the heavy elements that are later found in space between stars. The outer layers of the star are carried away at high speeds, forming the supernova ejecta. At large distances, this expanding shell interacts with the surrounding circumstellar medium and interstellar gas, creating the supernova remnant that can persist for many thousands of years as a visible or radio-bright structure. The remnant carries information about the explosion energy and the structure of the progenitor, but at this stage the focus remains on what happens near the center. Deep in the interior, the core that halts collapse and helps launch the shock then settles into a hot, dense proto-neutron star. Its mass is typically around 1.5 times that of the Sun, compressed into a region only tens of kilometers across. During the first tens of seconds after bounce, this object radiates the bulk of its gravitational binding energy as neutrinos. These neutrinos emerge from layers near the core in a process that gradually cools and leptonizes the matter, meaning that the number of electrons per baryon decreases as neutrinos escape. The cooling causes the proto-neutron star to contract further, becoming even more compact. If the mass of the core remains below a critical value, it stabilizes as a neutron star. If too much mass falls back onto it from the infalling envelope, it instead collapses further into a black hole. The threshold between these outcomes depends on the equation of state of dense matter, a relation between pressure density and temperature that is not yet fully known at the densities reached in these cores. The emerging neutron star does not remain perfectly symmetric. Asymmetries in the explosion, in the accretion of late infalling material, and in the distribution of neutrino emission can give the star a recoil often called a natal kick. This kick imparts a high space velocity to the neutron star relative to its surroundings. Observations of pulsar-proper motions show that many neutron stars move very rapidly through the galaxy, supporting the idea that core collapse events are often asymmetric. The same asymmetries imprint structure on the expanding ejecta, leading to clumps and jets in the supernova remnant. Gravitational waves, ripples in space-time, are also produced by these time-dependent asymmetries in the core, although for typical core collapse events they are weak, and only explosions in the nearby universe fall within reach of current detectors. To understand these complex processes, researchers combine detailed simulations of core collapse with observations across many wavelengths, and in rare cases with direct detections of neutrinos from nearby supernovae. A burst of neutrinos from a core collapse event in the neighbouring Large Magellanic Cloud provides strong evidence that a compact neutrino cooled core forms and releases most of the gravitational energy. Since that detection, numerical models grow more sophisticated, incorporating multidimensional hydrodynamics, improved neutrino transport, and realistic progenitor structures. These models reproduce many of the qualitative features of observed supernovae and yield neutron star masses, explosion energies, and remnant structures in broad agreement with data, though uncertainties remain. Within this framework, the birth of a neutron star is understood as the outcome of a sequence in which an iron-rich core collapses, a shock forms and stalls, neutrino heating and fluid motions revive it, and the outer layers are expelled while the central core settles into a hot, dense, rapidly cooling compact object. This newly formed core then begins its later evolution on longer timescales, but at the moment of its birth it is defined mainly by its mass radius, internal composition, rotation, and magnetic field, all inherited in complex ways from the progenitor star and the dynamics of the collapse and explosion. After the core collapse and the launch of the supernova shock, the compact object that remains at the centre settles into its identity as a neutron star, treated now as a single, self-contained body in space. In the first moments after its birth, it is still extremely hot, with temperatures in its interior reaching many billions of degrees Celsius. At these conditions, matter is a dense fluid of neutrons, protons, electrons, and trapped neutrinos. The star is not yet in the quiet long-term state often imagined when thinking of a neutron star. Instead, it is a proto-neutron star that is contracting, cooling, and adjusting to the balance between gravity and internal pressure. Its gravitational field is already very strong. The mass of this object is typically of the same order as the mass of the Sun, or somewhat larger, but it is compressed into a sphere only a few tens of kilometers in diameter. This compact size means that the surface gravity is enormous. A small change in height near the surface corresponds to a large change in gravitational potential, and the escape speed, the speed required to leave the star and not fall back, is a substantial fraction of the speed of light. General relativity, the theory that describes gravity at high densities and strong fields, is essential for describing this object accurately. Light leaving its surface is redshifted, meaning that its wavelength is stretched by the gravitational field. time itself runs more slowly close to the surface than it does far away. These effects are not details added to an otherwise Newtonian star. They are central to the way the neutron star behaves as a whole body. Inside, the pressure is provided mainly by degenerate nucleons, a term that indicates that neutrons and protons are packed so closely that quantum mechanical rules about how identical particles can share states dominate their behavior. At the densities reached in the deep interior, the average spacing between particles is comparable to the size of atomic nuclei. The relation between pressure, density, and temperature in this regime is described by an equation of state of dense matter, which is constrained by nuclear physics experiments and by observations of neutron star masses and radii, but is not yet known in complete detail. Different possible equations of state predict slightly different mass-radius relations for neutron stars, and observations of heavy neutron stars with masses significantly larger than that of the Sun place strong limits on how soft or stiff the equation of state can be. In all reasonable models, however, the star remains compact and supported against further collapse by the combined effects of nuclear forces and degeneracy pressure. During the first tens of seconds after core bounce, the proto-neutron star loses energy mainly by emitting neutrinos. These particles stream out from the dense interior, carrying away most of the gravitational binding energy that was released when the core collapsed from a large stellar radius to a compact neutron star size. As the star radiates neutrinos, it cools and contracts. This contraction is modest in terms of radius, but important for the internal density and pressure. The composition also changes as trapped neutrinos escape, and electron capture reactions continue, leading to a neutron-rich interior with only a modest fraction of protons and electrons. As the temperature drops, the outer layers begin to transition from a hot fluid to a more ordered state, and over the next minutes to hours a thin solid crust can start to form at the surface, although the detailed structure of that crust is better examined later. At the same time, the neutron star retains angular momentum inherited from the progenitor core. Because the core has collapsed from a region thousands of kilometers across to one with a radius of only tens of kilometers, conservation of angular momentum naturally produces rapid rotation. Even if the progenitor core rotated only moderately, the resulting neutron star can spin many times per second. Some newborn neutron stars are thought to rotate even faster, with periods of only a small fraction of a second. This rotation is not always uniform throughout the star. Differential rotation, where the inner regions spin at slightly different rates than the outer layers, can arise during collapse and early settling. Hydrodynamic and magnetic torques gradually redistribute angular momentum, working toward a more uniform rotation profile over time. But in the early phases, the object can host complex internal motions and oscillations related to its rapid spin. Magnetic fields are also an integral part of the newborn neutron star. The progenitor star likely contained magnetic fields generated by motions in its ionized gas. When the conducting core collapses, these fields are compressed and can be greatly amplified. Additional amplification can occur through dynamo processes driven by convection and differential rotation in the proto-neutron star. The result is a strong global magnetic field that threads the star and extends into the surrounding space. Typical field strengths are far higher than those found on ordinary stars, and in some cases they reach values so large that they influence the behavior of matter and radiation at a fundamental level. At this stage, the magnetic field is anchored in the highly conducting fluid interior and evolves slowly compared with the initial rapid cooling. The combined presence of strong gravity, rapid rotation, and intense magnetic fields defines the neutron star as a compact astrophysical laboratory. The star can support various normal modes of oscillation in which its fluid interior and forming crust vibrate in characteristic patterns. Some of these oscillations are excited during the collapse and bounce, and can radiate energy and gravitational waves, although for typical neutron star births these waves are weak at Earth. Internally, convection continues for some time, transporting heat outward and influencing the distribution of composition and magnetic fields. Over the first minutes, hours and days, these processes gradually die down as the star approaches a more static configuration. The cooling history of the neutron star as a whole object extends beyond the initial neutrino bright phase. After the first tens of seconds, neutrino emission from the interior continues to dominate energy loss for many thousands of years. Different microscopic processes, such as the modified or direct version of a reaction, in which neutrons change into protons and back, while emitting neutrinos control the cooling rate. Which processes operate most strongly depends on the internal composition, the presence or absence of superfluid phases, and the exact equation of state. Observations of young neutron stars in supernova remnants, where their surface temperatures can sometimes be inferred from X-ray spectra, provide clues to this cooling behavior. By comparing measured temperatures and ages with model predictions, astrophysicists constrain the physics of dense matter that governs the entire star. On larger timescales, the neutron star as a whole object can undergo gradual changes in its observable properties as it loses rotational energy and in some cases magnetic energy. Even before considering detailed emission mechanisms, one can think of the star's rotational kinetic energy and magnetic field energy as reservoirs that can power different phenomena. The star may slow its spin through the emission of radiation, and particle winds, and its field may decay or rearrange on long timescales. Some neutron stars likely receive additional mass from fallback of supernova ejecta in the first minutes or hours after the explosion. This fallback can temporarily bury magnetic fields under newly accreted material or change the final mass and spin of the object. In extreme cases, too much fallback can push the mass of the proto-neutron star above the maximum allowed by the equation of state, causing it to collapse further into a black hole. In many cases, however, the fallback mass is modest, and the neutron star survives as a stable compact object. The ensemble of these processes means that the newborn neutron star, while already recognizably a neutron star as a compact self-gravitating body, is not yet the quiet, slowly evolving object of later stages. It passes through a phase of rapid cooling structural adjustment and internal motion that sets its basic global parameters, its final mass and radius, its rotation rate, its overall magnetic field, strength, and the broad outline of its internal composition. Once these are established, the neutron star enters a longer era in which it behaves as a persistent, long-lived object in the galaxy, carrying the imprint of its birth conditions in its spin field and thermal state. In this view, the star is understood as a single entity that has emerged from collapse, now defined by strong gravity, high density, rapid rotation, and intense magnetism, ready to interact with its surroundings and to serve as a natural probe of matter in conditions that cannot be reproduced in ordinary laboratories. As a neutron star emerges from its early cooling phase and begins its long life as a stable compact object, one of its most important global properties is rotation. The star retains angular momentum from the collapsing core, so it spins rapidly about an axis. Because it is so compact, even a moderate initial rotation in the progenitor core becomes a high spin rate in the neutron star, with periods often measured in fractions of a second. This rotation is remarkably stable over many cycles, so that the star behaves like a precise cosmic clock. At the same time, the strong magnetic field of the neutron star is usually tilted relative to its rotation axis. Charged particles move in this combined gravitational and magnetic environment and emit radiation that is beamed along particular directions. When these beams pass across Earth during each rotation, telescopes record a series of pulses at regular intervals. Objects that show this behavior are called pulsars. In this view, a pulsar is simply a rotating neutron star whose magnetic geometry and orientation allow some of its radiation beams to intersect the line of sight. The arrival times of the pulses from a given pulsar can be measured with very high accuracy. Once the spin period is known, radio observatories and in some cases X-ray and gamma-ray instruments track the pulses over months and years. The sequence of arrival times can be fitted with a simple model in which the star's rotation gradually slows over time. This slow decrease in spin rate, called spin down, arises because the star is losing rotational energy. The main channels for this loss are electromagnetic radiation and particle winds flowing from the magnetized rotating star. The rate of spin down depends on the strength of the magnetic field, the rotation rate, and the way in which currents flow in the magnetosphere. By measuring both the period and its rate of change, astronomers infer characteristic ages and approximate magnetic field strengths for pulsars, treating the neutron star as a whole, rotating object. Many pulsars show an extraordinary level of rotational stability. For the most regular ones, the timing behavior rivals or exceeds the precision of atomic clocks over long timescales. This stability makes them valuable tools for many areas of astrophysics. Arrays of millisecond pulsars, which are particularly fast-spinning neutron stars with very stable periods, are used to search for long wavelength gravitational waves that stretch and squeeze the space-time between Earth and the pulsars. Any passing waves would imprint tiny shifts in the arrival times of pulses in a correlated way across the sky. The use of pulsars as timing references depends on the fact that the underlying neutron stars maintain their spin with only gradual predictable changes over long periods. However, not all pulsars behave in this perfectly smooth fashion. Many show small irregularities in their rotation. One common type of irregularity is called timing noise, a slowly varying departure from a simple spin-down model that may reflect complex processes in the star's interior or magnetosphere. Even more striking are events known as glitches. During a glitch, the pulsar's rotation rate suddenly increases by a small amount, after which the spin-down resumes sometimes with a modified rate. These events are interpreted as signs of an internal adjustment in the star, perhaps involving the transfer of angular momentum between a superfluid component of the interior and the more rigid crust. Although the detailed microphysics will be examined in later sections at this level, the glitch is observed as a sudden step in the whole star's rotation, followed by a relaxation toward a new long-term behavior. The pattern of glitches and timing noise varies from one pulsar to another, providing clues about differences in their internal structure and age. Pulsars are observed across the electromagnetic spectrum. Radio pulsars are the most numerous known class and were the first to be identified, but some neutron stars also show pulsations in X-rays and gamma rays. In certain objects, the radio beam is weak or absent, while high-energy pulses dominate, and in others, the opposite is true. These differences reflect variations in how and where particles are accelerated and emit radiation in the magnetosphere and near the surface, but at this stage they can be summarized as different observational windows on the same rotating neutron star. The pulse profiles, meaning the detailed shape of brightness, as a function of rotation phase, often show multiple peaks and components. Each component corresponds to radiation from different regions tied to the star's magnetic geometry. As the neutron star spins, these regions sweep around, and their varying visibility produces the observed pattern. Long-term changes in the pulse profile, or in the relative strength of different components, can indicate that the distribution of currents or the structure of the magnetosphere has evolved even if the global spin-down continues smoothly. The population of pulsars spans a wide range of spin periods and magnetic field strengths. Young pulsars born in recent supernovae tend to spin relatively rapidly and have strong magnetic fields. Over time, they lose rotational energy and slow down. The path traced in a diagram that compares spin period with its rate of change reflects this evolution. Some older neutron stars, however, are found with very short spin periods and comparatively low inferred magnetic fields. These are millisecond pulsars thought to have been spun up by long-term accretion of matter from a companion star in a binary system. In that phase, material spirals onto the neutron star, transferring angular momentum and increasing its rotation rate. Once accretion ends or becomes very weak, the star can shine as a rapidly rotating radio pulsar whose stability makes it a precise clock. In this way, millisecond pulsars record a history in which the whole neutron star has been recycled, with its spin rebuilt through interaction with its environment. Binary systems that host pulsars offer a particularly rich field for studying neutron stars as whole objects. When a pulsar orbits another star, careful timing of its pulses reveals the motion of the neutron star around the system's center of mass. Changes in arrival times encode the orbital period, the shape of the orbit, and often the mass of the companion. In some systems where the companion is another neutron star or a white dwarf, the gravitational interaction is strong enough that small relativistic effects must be included to match the timing data. These effects include the gradual rotation of the orbit's orientation and the decay of the orbital period due to gravitational wave emission. Observations of such systems have provided some of the most direct evidence for gravitational waves and have allowed precise tests of general relativity in the strong field regime. Throughout these analyses, the neutron star is treated as a point mass, with a well-defined rotation reinforcing the view of it as a coherent self-gravitating body whose bulk properties can be probed through timing. The way in which pulsars switch their emission on and off, or change mode over time, also illustrates aspects of the global neutron star state. Some pulsars exhibit nulling periods during which their pulses vanish for several rotations before reappearing. Others show mode changing, where the pulse profile alters abruptly between distinct patterns. There are also intermittent pulsars that switch between active and nearly silent states on much longer timescales, accompanied by changes in spin-down rate. These behaviors suggest that the global configuration of currents and fields in the magnetosphere can reorganize, changing how efficiently rotational energy is converted into radiation and particle outflows. While the detailed mechanism involves plasma processes around the star, the result is experienced as a change in the whole star's observable behavior, linking the internal rotation, the magnetic field, and the surrounding charged particles into a single system. Over millions to billions of years, many neutron stars slow their rotation to the point where their emission mechanisms become inefficient, or their beams no longer cross Earth. These older neutron stars may fade below detection thresholds and join a largely invisible population of slowly spinning compact remnants. Their existence is inferred from population studies and theoretical models that trace the birth and evolution of neutron stars in the galaxy. Even when undetectable as pulsars, they remain massive compact objects whose gravity and in some cases residual heat still influence their surroundings. A complete understanding of neutron stars as a galactic population must therefore account for both the visible pulsars and this quieter background of slowly rotating remnants. Throughout this section, the focus stays on the neutron star as a whole, rotating magnetized body whose regular pulses and timing behavior reveal its spin magnetic field and long-term evolution. Later, more detailed views will consider how the magnetosphere and radiation zones are structured, and how the star's surface and interior respond to the stresses generated by rotation and magnetic fields. Here, the central picture is that of a compact stellar remnant acting as a stable, though sometimes subtly variable clock in space, converting stored rotational energy into radiation and particle flows that can be traced and measured across great distances. Among the many rotating neutron stars in the galaxy, A small subset stands out because their magnetic fields are far stronger than those of typical pulsars. These objects are known as magnetars. In this view, a magnetar is treated as a whole neutron star in which magnetic energy dominates much of the observable behavior. Its field strength at the surface is thought to reach values that are several orders of magnitude higher than those of ordinary radio pulsars. At such field strengths, the magnetic field does not merely guide charged particles. It influences the structure of matter in the outer layers, the motion of particles near the star, and the way radiation is produced and transported. The magnetar still shares the basic properties of any neutron star, a mass comparable to, or somewhat larger than the mass of the Sun, a radius of only tens of kilometers, and a dense interior supported by nuclear forces and degeneracy pressure. However, its unusually strong field and particular rotational properties give rise to characteristic patterns of emission bursts and long-term evolution that distinguish it from other neutron stars when seen as a single interacting object. Observationally, magnetars reveal themselves through their persistent X-ray emission and their tendency to produce short, intense bursts, and more rarely giant flares of high-energy radiation. Many known magnetars are identified as anomalous X-ray pulsars or soft gamma repeaters. An anomalous X-ray pulsar is a neutron star whose X-ray brightness is higher than can be explained by the loss of rotational energy alone given its measured spin-down rate. A soft gamma repeater is characterized by repeated outbursts of soft gamma rays and hard X-rays. Over time, it has become clear that these two observational classes largely overlap and can be understood as different manifestations of the same underlying type of object, a highly magnetized neutron star whose magnetic field is decaying and rearranging, releasing energy in the process. In terms of spin, magnetars tend to rotate more slowly than many ordinary radio pulsars. Their spin periods are usually measured in several seconds rather than fractions of a second. Despite this relatively slow spin, they often show rapid spin down, implying that they lose rotational energy at high rate. When the observed period and its derivative are used in simple models of magnetic braking, the inferred dipole magnetic fields are extremely strong. This suggests that the external large-scale magnetic configuration of a magnetar has a strong dipole component. However, the full magnetic structure likely includes higher-order components and complex internal fields that cannot be directly measured. The high spin-down power and strong field provide a large reservoir of magnetic energy that can be tapped to power persistent emission and bursts. The persistent X-ray luminosity of a magnetar is often higher than what would be expected if the star were powered only by the gradual loss of rotational energy. This points to an additional energy source understood as the decay and reconfiguration of the magnetic field itself. Within the star, the field is anchored in highly conducting matter. As the field evolves, stresses build up in the solid outer layers and in the magnetized fluid beneath. These stresses can lead to slow plastic flow or to sudden failures in which parts of the outer crust give way and adjust to a new configuration. When such a rearrangement occurs, it can trigger a release of energy that heats the surface and magnetosphere, leading to an outburst. The star as a whole responds through changes in its emission, sometimes accompanied by small changes in rotation rate. The bursts seen from soft gamma repeaters are thought to reflect such sudden releases of magnetic energy, often involving only a small fraction of the total stored field, but still producing intense high-energy flashes. Giant flares represent more extreme events in which a much larger amount of magnetic energy is converted into radiation in a very short time. During a giant flare, the magnetar's X-ray and gamma-ray output briefly rises to levels that far exceed its already bright, persistent luminosity. The flare typically begins with a very short, intense spike of hard radiation, lasting less than a second, followed by a longer tail of softer X-rays that decays over several minutes. The tail often shows pulsations at the spin period of the magnetar, indicating that the emission region is anchored to the rotating star. The total energy released in a giant flare is enormous, rivaling the energy the Sun emits over a long interval, yet it represents only a modest fraction of the total magnetic energy stored in the magnetar's field. These flares are rare, and only a few have been detected in detail, but they provide strong evidence that magnetic stresses in a neutron star can reach and exceed the breaking point of its outer layers, causing a global adjustment. On longer timescales, magnetars show a range of variability patterns. Some spend extended periods in a relatively steady state, with persistent X-ray emission and regular pulsations at their spin period. Others undergo outbursts in which the luminosity rises by large factors for weeks or months before gradually returning toward a lower level. During an outburst, the X-ray spectrum pulse profile and spin-down rate can all change, indicating that the entire system of surface temperature distribution, magnetospheric currents, and external field configuration has been perturbed. Over years, the magnetic field is expected to decay, especially in the crust and outer core where electrical resistivity and other transport processes allow currents to dissipate. Field decay converts magnetic energy into heat, which helps maintain the high surface temperatures seen in magnetars compared with ordinary neutron stars of similar age. Modeling this evolution requires detailed microphysics, but at the level of the whole star, the picture is that of a compact object whose long-term thermal and radiative behavior is controlled by the gradual rearrangement and decay of its strong field. The connection between magnetars and the broader neutron star population emerges when their locations and ages are examined. Many magnetars are found in or near regions of recent star formation, such as young star clusters and supernova remnants, indicating that they are relatively young objects on cosmic timescales. Their characteristic ages inferred from spin period and spin-down rate often fall in the range of thousands to tens of thousands of years. This suggests that the most extreme magnetic fields appear soon after birth and then decay significantly as the neutron star ages. It is likely that only a fraction of massive stars produce magnetars, perhaps those that maintain rapid rotation and strong internal magnetic fields in their cores at the time of collapse. The exact conditions that lead to magnetar formation remain uncertain, but the association with young stellar environments and supernova remnants supports a link with particular progenitor properties, rather than magnetars being simply a late stage in the evolution of all neutron stars. Magnetars also interact with their surroundings as whole compact objects. Their strong magnetic fields and high energy emission drive powerful particle outflows, forming winds that can carve cavities in the surrounding medium and inflate nebulae in some cases. These nebulae, sometimes seen as extended X-ray or radio emission around the magnetar, record the history of energy output over thousands of years. The high-energy photons and particles from magnetars can ionize and heat nearby gas, influencing the local interstellar environment. In binary systems, if any exist with confirmed magnetars as members, the interaction between the magnetar's field and a companion's wind or accretion flow would be expected to produce distinctive observational signatures, but such systems are rare, and their properties are still being explored. From a theoretical standpoint, magnetars provide a way to test how matter and radiation behave in magnetic fields that are strong enough to approach or exceed critical quantum values. In such fields, quantum electrodynamics predicts modifications to the behavior of photons and charged particles, including effects such as vacuum polarization. These effects alter how radiation propagates near the star and can leave imprints on polarization and spectral features. Observations of magnetar emission, especially in X-rays combined with models of radiative transfer in strong fields, therefore serve not only to describe these particular neutron stars, but also to probe fundamental physics in regimes inaccessible in terrestrial laboratories. uncertainties remain about many aspects of magnetar behavior. The exact geometry of the internal and external magnetic fields, the detailed sequence of events leading to bursts and flares, and the long-term fate of magnetars as they age are all active areas of research. Some models suggest that as the fields decay, magnetars may evolve into more ordinary-looking neutron stars with lower surface fields and weaker emission. Others emphasize the possibility of different evolutionary channels, depending on initial field strength, mass, and internal composition. Despite these open questions, the broad picture is clear: magnetars are neutron stars in which magnetic energy is the dominant driver of observable phenomena, from persistent X-ray luminosity to sudden bursts and rare giant flares. In this section, the magnetar is viewed as a compact rotating, strongly magnetized star whose global field and rotation together power its emission and drive its evolution, forming one extreme end of the continuum of neutron star behavior that spans from ordinary radio pulsars through high-energy pulsars to these rare but highly energetic magnetic stars. Many neutron stars do not evolve in isolation, but share their lives with companion stars, and in these systems the behavior of the neutron star as a whole object is shaped by the exchange of mass and angular momentum within the pair. Such binaries arise when a massive star that will eventually form a neutron star is born in orbit around another star, or when dynamical interactions in dense clusters later assemble a compact object and a companion into a bound system. When the primary undergoes core collapse and leaves a neutron star, the sudden mass loss and any natal kick can disrupt the orbit entirely, but in some cases the binary survives, now containing a compact remnant and a still luminous companion. Over time, winds from the companion or direct overflow of its outer layers under gravity can feed gas onto the neutron star. This accretion process turns gravitational energy into radiation, and by transferring angular momentum changes the spin and sometimes the magnetic properties of the neutron star as a unified body. Neutron star binaries are commonly divided into systems with high-mass companions and those with low-mass companions, reflecting differences in how mass is supplied. In a high-mass X-ray binary, the companion is typically an early-type star with strong stellar winds, or a disk of gas around it. The neutron star moves through this outflow and captures a fraction of the gas that passes near it. As the gas falls into the deep gravitational potential of the compact star, it gains kinetic energy and heats to high temperatures. Much of this energy is radiated in X-rays from regions near the neutron star, making the system a bright X-ray source. The neutron star's rotation and magnetic field guide the gas onto its magnetic poles, often producing beams of X-ray emission that vary with the spin period. In such accretion-powered pulsars, the observed pulses trace the rotation of the neutron star, just as in rotation-powered pulsars, but now the energy source is mainly the gravitational energy of infalling matter rather than the star's rotational energy reservoir. The structure of the binary orbit influences how steady this accretion is. In wide systems with eccentric orbits, the neutron star may encounter denser parts of the companion's wind or equatorial disk only near periastron, the point of closest approach, leading to periodic outbursts. In tighter systems, accretion can be more continuous, and the neutron star experiences a steadier flow of mass and angular momentum. In low-mass X-ray binaries, the companion is a star with a mass comparable to or lower than that of the Sun. The neutron star's gravity can pull material directly from the companion if the latter fills its gravitational domain, called its Roche lobe. Gas then streams toward the neutron star and forms an accretion disk as it spirals inward under conservation of angular momentum. In the disk, viscous processes gradually transfer angular momentum outward and allow matter to drift inward, heating the gas to high temperatures. The inner regions of the disk and the boundary layer where the disk matter meets the neutron star surface radiate strongly in X-rays. From the perspective of the neutron star, this disk is a conduit that delivers mass and angular momentum, spinning the star up over long timescales. Many of the fastest known millisecond pulsars are thought to have been recycled in this way, having spent an extended period in a low-mass X-ray binary state, where accretion gradually increased their spin to hundreds of rotations per second. Once accretion slows or stops, the neutron star can shine again as a rotation-powered radio pulsar, but now with a much shorter period and often with a lower inferred dipole magnetic field, perhaps reduced by processes that bury or rearrange the surface field during the accretion phase. Some systems show transitional behavior between an accretion-powered state and a rotation-powered state on relatively short timescales, highlighting how the whole neutron star responds when the balance between inflowing matter and its own radiation and particle wind changes. Accretion onto a neutron star in a binary system can also ignite thermonuclear reactions in the accreted material on its surface. In some low-mass X-ray binaries, hydrogen and helium-rich gas accumulates on the neutron star until conditions at the base of the layer become hot and dense enough for runaway nuclear burning. This burning releases energy rapidly producing type 1 X-ray bursts, sudden increases in X-ray brightness that rise in seconds and decay over minutes. During these bursts, the neutron star as a whole object responds to the rapid heating and cooling of its outermost layers, and the burst-like curves and spectra provide information about surface gravity, composition, and heat transport. In some cases, oscillations at or near the spin frequency appear during bursts, allowing measurements of the neutron star rotation even when persistent pulsations are weak or absent. The occurrence and properties of such bursts depend on the accretion rate, the composition of the inflowing material, and the structure of the neutron star surface and outer envelope. But at this level they can be seen as global responses of the star to episodic nuclear energy release on top of steady accretion. Binary neutron star systems, in which both components are compact objects, offer another view of whole star behavior in shared orbits. When a neutron star orbits a white dwarf or another neutron star, its gravitational influence can be measured through high-precision pulsar timing. In double neutron star binaries where one or both members are pulsars, the arrival times of pulses reveal not only the orbital period and eccentricity, but also relativistic effects such as the advance of periastron and the decay of the orbit due to gravitational wave emission. The rate of orbital decay matches the predictions of general relativity when gravitational waves carry away energy and angular momentum from the system, causing the two neutron stars to spiral slowly closer together. Over time, such systems are expected to merge, forming a single compact object and ejecting neutron-rich matter. Observations of merging neutron stars through both gravitational waves and electromagnetic signals confirm that these binaries exist and evolve as anticipated. In this section, however, the focus remains on the pre-merger binary as a bound system where the neutron star's global properties can be measured and its mass constrained by the orbital dynamics. Precise mass measurements from pulsar binaries have shown that neutron stars can reach masses significantly higher than that of the Sun while remaining stable, providing strong constraints on the allowed equations of state for dense matter. Neutron star binaries evolve under the combined influence of mass transfer gravitational radiation, magnetic braking, and interactions with their surroundings. High-mass X-ray binaries often trace relatively young stellar populations and can be found near star-forming regions in the galactic disk. Their lifetimes are limited by the evolution of the massive companion, which may eventually explode as a supernova itself, possibly leaving a double compact object or disrupting the system. Low-mass X-ray binaries and recycled pulsars tend to be associated with older stellar populations, including globular clusters and the galactic bulge, where dynamical interactions and long timescales allow many opportunities for binary formation and transformation. In dense clusters, close encounters between stars and compact objects can exchange partners and alter orbital parameters, enriching the variety of neutron star binaries and their evolutionary paths. Throughout these changes, the neutron star remains a compact self-gravitating body whose mass, spin and magnetic field respond to the inflowing or outflowing matter. In some phases, accretion dominates, and the star's spin increases while its observed emission reflects the release of gravitational and, in some cases, nuclear energy. In others, the neutron star's own rotation-powered emission controls its interaction with any residual accretion flow, sometimes blowing away incoming material and re-establishing a rotation-powered pulsar state. The system can move between these modes in response to relatively modest changes in accretion rate, highlighting the tight coupling between the star's internal energy reservoirs and its environment. These binary interactions also leave long-term imprints on the neutron star population as a whole. The existence of many millisecond pulses with small spin-down rates and often in binary systems supports the view that recycling through accretion is a common pathway. The distribution of neutron star masses measured in binaries suggests that some stars accrete enough material to increase their mass significantly after birth, pushing them closer to the maximum stable mass, and thus providing important data points for dense matter physics. The variety of X-ray light curves and spectra seen from neutron star binaries reflects differences in accretion geometry, magnetic field strength and spin, but in all cases the central gravitational engine is the same, a compact neutron star whose deep potential well and rapid rotation dominate the flow of matter and the production of high-energy radiation. In this way, binaries extend the range of environments in which neutron stars can be studied as whole objects, offering multiple channels through which their masses spins and magnetic fields can be measured, and through which their interaction with surrounding matter can be traced over many stages of stellar and galactic evolution. Around every rotating magnetized neutron star there is a region of space in which its magnetic field and rotation control the motion of charged particles. This region is called the magnetosphere. In this view, the magnetosphere is treated as a global structure that extends from the stellar surface out to distances where the magnetic influence weakens and other forces become more important. The basic configuration is often approximated as a tilted dipole field, similar in shape to the field around a simple bar magnet but anchored to a compact star that spins rapidly. As the neutron star rotates, the magnetic field lines near the star are carried around with it, and because the surrounding space is filled with plasma, the motion of the field and the motion of the charged particles are tightly linked. The magnetosphere is therefore not an empty region with static lines, but a filled dynamic structure where electric and magnetic fields, plasma flows and rotation all interact. Close to the neutron star, the magnetic field is very strong and has a simple, nearly dipolar shape. Field lines emerge from one magnetic pole loop through space and re-enter the star near the opposite pole. In this inner region, the plasma tends to correlate with the star, meaning that charged particles are tied to the field and move around the axis of rotation at the same angular rate as the neutron star itself. The electric field induced by the rotating magnetic field acts to enforce this correlation by adjusting the distribution of charges. A particular charge density called the correlation density, often described using a theoretical model, specifies how many charged particles of which sign are needed at each point to cancel the component of electric field that would otherwise accelerate particles along the magnetic field lines. When the plasma supply is sufficient, the magnetosphere can approach this ideal correlating state over a wide region. Further out there is a special distance from the star called the light cylinder, where a point correlating with the star would have to move at the speed of light to keep up with the rotation. At distances larger than this rigid correlation is impossible. The light cylinder radius therefore marks a natural outer boundary for certain magnetospheric structures. Magnetic field lines that are closed, meaning they loop back onto the star, without crossing the light cylinder, define an inner closed zone. In contrast, field lines that extend beyond the light cylinder and do not return define an open zone. Particles moving along these open field lines can escape to large distances, carrying energy and angular momentum away from the star. The division between closed and open field lines is central to the magnetosphere's global geometry and to its ability to launch winds. The plasma that fills the magnetosphere must come from somewhere. The strong electric fields induced by rotation can pull charged particles from the neutron star surface or from a thin atmosphere, especially near the magnetic poles where field lines are nearly open. Once some particles are present, they can be accelerated to high energies by any unscreened electric field components along the magnetic field lines. These primary particles emit high-energy photons through curvature radiation or inverse Compton scattering as they follow curved field lines. Some of these photons interact with the intense magnetic field or with other photons to produce electron-positron pairs, which are pairs of a negatively charged electron and its positively charged antimatter counterpart. This pair creation process can occur repeatedly, leading to cascades that multiply the number of particles. In this way, small initial populations of charges can seed dense plasma populations that help fill the magnetosphere, allowing it to approach the correlation density in many regions, while still leaving gaps where acceleration continues. The magnetosphere naturally separates into several characteristic zones, defined by how field lines connect to the star and how plasma flows. Near each magnetic pole, open field lines emerge from a region on the surface often called the polar cap. These lines thread the light cylinder and extend outward into a larger scale pulsar wind. The polar caps are surrounded by rings of closed field lines that loop back to the star. Above the polar caps and along open field lines, acceleration zones can form where the local charge density departs from the correlation value, and electric fields along the magnetic field become strong. Further out near the boundary between open and closed field regions and near the light cylinder, additional gaps can appear where field geometry and charge supply allow sustained electric fields. Although detailed models differ in the exact shapes and locations of these zones, they generally agree that the magnetosphere is structured by the interplay between rotation field, geometry, plasma supply, and global current systems. The rotation of the neutron star and the presence of free charges also imply the existence of large-scale electric currents flowing through the magnetosphere and closing through the star and any surrounding wind. These currents are not minor corrections but integral parts of the global field structure. They can modify the dipole field, especially near the light cylinder and in the region where open field lines bend back to form an extended current sheet. In this current sheet, which lies roughly in the equatorial plane beyond the light cylinder, magnetic field lines of opposite polarity come into close contact and can reconnect, changing their connectivity and releasing magnetic energy. The outflow of plasma and fields in this region contributes to the superfast wind that carries energy from the neutron star into the surrounding space. The shape of the magnetosphere is generally three-dimensional and depends on the angle between the rotation axis and the magnetic axis. In an aligned rotator where the axes are nearly parallel, the field structure can be approximately symmetric around the rotation axis, though even in that case rotation distorts field lines near the light cylinder and forms a spiral-shaped wind. In an oblique rotator where the magnetic axis is tilted, the magnetosphere becomes more complex and time-dependent, with the field configuration changing as the star turns. This time dependence is essential for generating the sweeping beams seen as pulsar emission. But even without considering radiation, it means that the magnetosphere is not a static configuration, but a rotating pattern of fields and currents. Numerical simulations using magnetohydrodynamics and more detailed plasma models have been developed to explore these structures. They confirm that open field lines are twisted into spiral shapes beyond the light cylinder, and that current sheets form where the field reverses direction. They also show that the closed zone can be compressed or expanded, depending on the balance between rotational energy loss and plasma loading. Although the details differ from one model to another, a common feature is that the magnetosphere self-adjusts to a configuration where it can steadily extract rotational energy from the neutron star and channel it into outgoing electromagnetic fields and particle flows. The strength of the magnetic field and the rotation rate both influence the size and character of the magnetosphere. In a strongly magnetized, slowly rotating neutron star, the light cylinder lies at a large distance compared with the star's radius, and the closed zone can occupy a substantial volume. The field near the star dominates over other influences, and the magnetosphere may be filled with dense plasma that enforces corrotation over a wide region. In a rapidly rotating pulsar with a more moderate field, the light cylinder is closer, and a larger fraction of the magnetic flux can be open, supporting a powerful wind. Magnetars, with their intense fields, may host magnetospheres in which higher-order multipole components and strong twisted field structures near the star play an important role. In those cases, the magnetosphere can store significant magnetic energy in non-potential configurations that may be released suddenly when the field relaxes, although the details of those processes involve both the magnetosphere and the outer layers of the star. The magnetosphere also interacts with any external plasma that flows past the neutron star. In systems where the neutron star moves through the interstellar medium or through a stellar wind from a companion, the external flow can confine or distort the outer parts of the magnetosphere and the pulsar wind. This interaction can produce a bow shock and a trail of shocked gas, forming a pulsar wind nebula where the magnetospheric outflow deposits its energy. In accreting systems, the inner edge of an accretion disk may be truncated at the point where the magnetic pressure of the neutron star field balances the ram pressure of the inflowing gas. Inside this truncation radius, the magnetosphere controls how gas is funneled toward the star, often channeling it along field lines toward the magnetic poles. In all these cases, the magnetosphere acts as the interface between the neutron star and its environment, mediating how energy and angular momentum are exchanged. The global magnetospheric structure evolves over time as the neutron star spins down, and in some cases as its magnetic field decays or rearranges. As the rotation rate decreases, the light cylinder moves outward, altering the balance between open and closed field line regions. The total power carried away by electromagnetic fields and particle winds decreases, and the magnetosphere becomes less energetic. If the large-scale field weakens, the overall size of the magnetically dominated region shrinks. Yet even old neutron stars with long spin periods and lower fields can maintain magnetospheres, albeit less luminous and harder to detect. Throughout its life, the neutron star is thus surrounded by a structured region of plasma and fields that reflects its rotation, magnetic strength, and history of interaction with its surroundings. In this section, the focus remains on the magnetosphere as a global structured extension of the neutron star's magnetic field into space filled and shaped by plasma that corrotates streams outward along open lines or participates in large-scale currents. This structure provides the framework within which radiation beams, high-energy emission zones, and particle winds arise, and it defines the way in which the compact star communicates its rotational and magnetic energy to the wider environment. Within the structured magnetosphere surrounding a neutron star, there are regions where charged particles are accelerated, and where most of the observable radiation is produced. In this view, the star its magnetic field, and the surrounding plasma act together as a single system that converts rotational or magnetic energy into beams of radio waves, X-rays, gamma rays, and outflowing particle winds. The magnetic field lines guide the motion of electrons and positrons, and any electric field component along these lines can speed the particles up to very high energies. As they move along curved paths in the strong field, they emit curvature radiation, a form of light produced when charged particles follow bent trajectories at speeds close to the speed of light. They can also radiate through synchrotron emission, where particles spiraling around field lines lose energy as light, and through inverse Compton scattering, in which they transfer energy to lower energy photons. Each of these processes operates more strongly in particular zones of the magnetosphere, so that different heights and field line regions favor different parts of the spectrum. In many pulsars, radio waves are thought to come from regions above the magnetic polar caps where open field lines rise out of the stellar surface. In these zones, strong electric fields can appear because the actual charge density departs from the ideal correlation value. Primary particles accelerated, there can trigger cascades of pair creation that fill the open field region with dense plasma. Radio emission in this regime is believed to be coherent, meaning that many particles act together in phase to produce radiation much stronger than the sum of many independent emitters. The exact microphysics of this coherent process is still uncertain, and several models compete, but observations of narrow, bright radio pulses that often show fine structure and polarization support the idea that the radio beam originates in organized plasma motions tied to the open field lines. The height of this radio-emitting region above the surface is inferred from pulse shapes and polarization sweeps, and appears to vary among pulsars, but in all cases the emission is confined to a relatively narrow zone within the broad magnetosphere. Higher in the magnetosphere near the boundary between open and closed field lines, and closer to the light cylinder, charged particles can be accelerated in extended gaps, where the magnetic geometry and limited charge supply allow unscreened electric fields to persist. These outer magnetospheric zones are favorable sites for high-energy emission. In such regions, electrons and positrons moving along long curved trajectories emit gamma rays through curvature radiation, and produce further pairs when their photons interact with a strong field or with ambient light. Observations of gamma-ray pulsars show broad pulses that often peak at phases different from the radio pulses, suggesting that the high-energy beams originate at greater altitudes and along different field lines than the radio beams. Space-based gamma-ray telescopes detect many pulsars whose emission is dominated by this high-energy component, including some that are faint or even undetectable in radio, indicating that the main particle acceleration and radiation zones in these objects lie far from the stellar surface. Between the polar caps and the outer gaps, more narrow acceleration regions can form along the last open field lines. These so-called slot gaps extend from near the surface toward the light cylinder and can also host energetic particles that radiate across a wide range of frequencies. The combined effect of polar cap slot gap and outer gap emission creates complex pulse profiles, where different peaks correspond to radiation from different heights and magnetic longitudes. By modelling these profiles and comparing them with observed light curves, and polarization researchers map the likely locations of the radiation zones within the global magnetospheric structure. The outflowing particle wind is another crucial channel through which energy leaves the neutron star environment. Along open field lines that cross the light cylinder plasma can no longer correlate with the star, and instead is carried outward as part of a relativistic wind of electrons, positrons, and electromagnetic fields. Close to the star, this wind is dominated by electromagnetic energy, with particles tied to rapidly oscillating fields. Farther out interactions and instabilities can convert some of this electromagnetic energy into kinetic energy of the particles so that they stream away at high speed. Where this wind meets the surrounding medium, such as the interior gas of a supernova remnant, or the interstellar medium, it slows abruptly at a termination shock. Downstream of this shock, particles radiate synchrotron emission across radio-optical and X-ray bands, forming a pulsar wind nebula. The structure and brightness of such nebulae seen around some young pulsars record the history and geometry of the particle wind, and thus indirectly trace the long-term behavior of the magnetospheric outflow. In magnetars, the radiation zones differ in some respects from those of ordinary rotation-powered pulsars, because the magnetic field is so strong that it can twist and distort the magnetosphere. Currents flowing through twisted field lines can maintain strong electric fields and dense plasma in regions close to the star. Thermal photons from the hot surface scatter off these magnetospheric charges in a process called resonant scattering, gaining energy and creating a hard X-ray tail in the spectrum. During bursts and flares, sudden rearrangements of the field inject additional particles and energy into the magnetosphere, thickening the scattering region and altering the pulse shape. The persistent X-ray emission of magnetars is thus often interpreted as surface thermal radiation, modified by passage through an active magnetospheric layer, rather than as pure surface emission. Even in these extreme objects, however, the basic pattern of acceleration zones, currents and outflows remains tied to the global magnetic configuration and rotation. In accreting neutron stars, the interaction between the magnetosphere and incoming gas defines additional radiation regions. Where the inner edge of an accretion disk meets the stellar magnetic field, matter can be lifted from the disk plane and channeled along field lines toward the magnetic poles. As this material falls, it forms narrow accretion columns that end in bright hotspots near the surface. In these columns, gas decelerates in a radiative shock and emits intense X-rays. The beaming pattern from the columns and the rotation of the neutron star combine to produce X-ray pulsations. Outside the columns, scattered photons and a hot corona of electrons above the disk add further components to the spectrum. In such systems, high-energy light originates both very close to the surface and in the inner disk, but the magnetosphere still controls the flow of matter and sets the geometry of the emission zones. Across the neutron star population, particle winds and radiation zones evolve as spin and magnetic field change. Young, rapidly rotating pulsars with strong fields drive powerful winds and host bright magnetospheric emission from radio to gamma rays. As they age and slow, the potential drop available for particle acceleration decreases, pair cascades become weaker, and both high-energy emission and wind power decline. Some older neutron stars emit mainly thermal X-rays from their cooling surfaces with only modest magnetospheric contributions. Magnetars, with their decaying but still intense fields, maintain active magnetospheres and strong X-ray output for longer than ordinary pulsars of similar spin period, while recycled millisecond pulsars, despite their relatively low surface fields, can sustain efficient high-energy emission through rapid rotation and a favourable magnetospheric structure. In all cases, the radiation zones and winds are shaped by the underlying magnetic geometry, the available electric potentials and the supply of plasma, and they form the observable link between the compact star and its surroundings, transforming stored rotational or magnetic energy into streams of photons and particles that travel far beyond the light cylinder. At the outer boundary of a neutron star, the dense matter of the interior meets the emptier space around it, across a very thin surface layer and an even thinner atmosphere. In this view, attention rests on this boundary region, where gravity, temperature, magnetic fields and radiation join to shape what a distant observer can see. The neutron star as a whole remains extremely compact, so the surface gravity is enormous, many hundreds of billions of times stronger than gravity at the surface of Earth. Under such gravity, matter is held tightly to the star. Any irregularity in height corresponds to a large change in gravitational potential, so material that is not supported by internal stresses or magnetic fields quickly slides or flows until it reaches mechanical balance. As a result, the neutron star surface is very nearly spherical, with only modest deviations allowed even in regions where magnetic fields or local stresses are strong. Mountains, if they exist, are expected to rise only to heights of at most a few tens of centimeters to a few meters before the weight of the overlying material forces them down, although some models allow slightly larger structures in special circumstances. The outermost solid layer beneath the surface can support shear stresses, but the visible surface itself behaves effectively as a dense, nearly smooth boundary where radiation escapes. Above this boundary lies a layer that can be called an atmosphere, although it is unlike the familiar atmospheres of planets and ordinary stars. The neutron star atmosphere is extremely thin in geometric thickness, often measured in centimeters to perhaps a few meters, but it is very dense compared with terrestrial standards and is fully ionized, meaning that atoms are stripped into nuclei and electrons. Its composition depends on the star's history. An isolated neutron star that has not accreted recent matter from its surroundings may retain a light element atmosphere dominated by hydrogen or helium remnants of material left after birth, or produced by nuclear processes in the outer layers. In accreting systems, the surface can be covered by matter drawn from a companion star, so the atmosphere reflects the composition of that inflow, often hydrogen-rich, but potentially containing heavier elements. Over time, gravitational settling tends to bring heavier nuclei downward and leave the lightest elements near the top because the strong gravity separates species according to mass very efficiently. The temperature at the surface is high enough that thermal radiation emerges mainly in the X-rays for young neutron stars. Effective temperatures are typically in the range of several 100,000 to several million degrees Celsius, depending on age and internal cooling. At these temperatures, the peak of the thermal spectrum lies at photon energies much higher than visible light. However, the observed spectrum at infinity is not simply that of a perfect blackbody, because both the atmosphere and the gravitational field modify it. Photons climbing out of the deep gravitational potential lose energy, a process known as gravitational redshift, so that their wavelengths lengthen and their energies decrease between emission and detection. This redshift depends on the compactness of the star, the ratio of its mass to its radius, and provides one of the few ways to infer that compactness observationally when combined with models of the surface emission. The atmosphere itself imprints additional features. In a light element atmosphere, photons interact with free electrons and ions in ways that depend on energy direction and polarization. As a result, the emerging spectrum can be harder or softer than a simple blackbody at the same effective temperature, and may contain absorption features if certain ions are present in abundance. In strong magnetic fields, as found on most neutron stars, these effects become even more pronounced. The magnetic field quantizes the motion of charged particles, altering the possible energy levels in which electrons can move. This leads to cyclotron features, which are absorption or emission features at characteristic energies linked to the field strength, and to different opacities for light polarized parallel or perpendicular to the field. In such conditions, radiation tends to escape more easily along certain directions relative to the field lines, so the surface brightness becomes anisotropic, with some regions and angles brighter than others, even at fixed local temperature. The global magnetic geometry therefore leaves an imprint on the pattern of surface emission. General relativity further shapes how the surface is seen. The strong gravitational field of a neutron star bends the paths of light rays leaving the surface so that an observer at a great distance can see parts of the star that would be hidden in a purely Newtonian picture. In practice, this light bending means that more than half of the surface can be visible at once. A hotspot near the far limb may still contribute to the observed flux because its photons are bent around the star. This effect smooths out the rotational modulation of any surface temperature variations, reducing the contrast between the brightest and faintest phases of a pulse. Detailed modelling of pulse profiles therefore must include light bending to extract information about the sizes and locations of hotspots, and about the star's compactness. Hotspots arise when some parts of the surface receive more heat than others. One common cause is the impact of charged particles flowing along magnetic field lines, from the magnetosphere down to the magnetic poles. These return currents deposit energy in small regions, raising their temperature above the average. Another cause is accretion, in which gas channeled by the magnetic field onto the poles releases gravitational energy, where it strikes the surface, forming accretion-powered hotspots. In magnetars, stresses in the outer solid layers can lead to small fractures and rearrangements that heat localized patches from below, producing transient or persistent warm regions. In all these cases, the neutron star as a whole remains compact and nearly spherical, but its surface temperature map develops structure with hotter polar caps or streaks embedded in a cooler background. As the star rotates, these temperature inhomogeneities move in and out of view, giving rise to pulsations in X-ray light curves that can be used to infer the geometry of the magnetic field and the distribution of heating. The atmosphere mediates the emission from these hotspots. In a magnetized atmosphere, heat flows more easily along field lines than across them, so the shape of a hotspot can be elongated in the direction of the local field. The emergent spectrum from a hotter region may differ from that of the cooler surroundings, not only because of its higher temperature, but also because different layers become visible at different energies. Observations of X-ray pulsars and thermally emitting isolated neutron stars often show energy-dependent pulse shapes and phase shifts consistent with such atmospheric and geometric effects. By fitting these observations with models that include realistic atmospheres, gravitational redshift and light-bending researchers extract estimates of surface temperature distributions and constraints on mass and radius. In accreting neutron stars that undergo thermonuclear X-ray burst the surface and atmosphere temporarily respond to intense heating from below. During a burst, the outer layer where nuclear burning occurs is heated rapidly and expands, causing the apparent emitting area and the spectral temperature to change as a function of time. In some bursts, radiation pressure can become strong enough to lift the photosphere, the layer from which most photons escape, to larger radii before it settles back, a phenomenon known as photospheric radius expansion. These events provide additional ways to probe the surface gravity and compactness of the star, because the luminosity at which expansion occurs is related to the balance between radiation pressure and gravity in the atmosphere. Even outside bursts, the stability of nuclear burning in shallow layers depends sensitively on the local accretion rate and the thermal state of the outer envelope, tying surface phenomena to deeper thermal and compositional profiles. For very strong magnetic fields, some models suggest that the outermost layers of the neutron star may not form a conventional gaseous atmosphere at all, but instead condense into a solid or liquid surface, with only a very tenuous overlying layer. In such a case, the emission may emerge directly from a condensed surface with reflection and emissivity properties that differ from those of a gas. This scenario remains an area of active research, with uncertainties about how often such condensation occurs and under what combinations of field strength, temperature and composition. Some isolated neutron stars show thermal spectra that deviate from simple atmospheric models, prompting exploration of condensed surface and magnetized atmosphere combinations. Regardless of which detailed model applies in each case, it is clear that the surface region of a neutron star sits at the intersection of extreme gravity, strong magnetic fields, high temperature and dense plasma physics. From the point of view of a distant observer, This region defines the star's apparent size, color, and pulse shape. The light that leaves it carries information about surface gravity through gravitational redshift, and burst behavior about magnetic field strength through spectral features, and polarization, and about temperature distribution through rotational modulation. In this way, the surface and its thin atmosphere form the visible face of the neutron star, translating conditions in the compact object into observable signals that can be measured and interpreted directly at the boundary between dense matter and space. Beneath the thin atmosphere and the very outer surface of a neutron star, matter changes from a hot, partially gaseous layer into a solid or semi-solid crust in which atomic nuclei form an ordered structure. In this region, the crushing gravity of the star and the intense pressure from the overlying material force matter into states far denser than anything found in ordinary planetary rocks or metals, yet the material still retains a recognizable lattice of discrete nuclei embedded in a sea of electrons. This lattice, sometimes called a Coulomb crystal, forms because positively charged nuclei repel one another and arrange themselves in a pattern that minimizes their total energy under the confining pressure. The electrons freed from individual atoms by the high density and temperature move through this lattice as a highly degenerate gas, meaning that quantum rules determining which states they can occupy dominate their behavior. Together, the nuclei and electrons create a solid that is extremely stiff and dense, able to support shear stresses and carry electric currents, and they form the outer shell of the neutron star's dense interior. Near the top of the crust, just below the atmosphere, densities are still low enough that the nuclei resemble familiar atomic nuclei, though they are fully ionized and stripped of their surrounding electrons. At these depths, the composition may be dominated by iron group elements, or by lighter nuclei left from earlier stages of stellar evolution or surface burning, depending on the history of the star and any accretion it has experienced. As one moves deeper into the crust, the pressure rises rapidly because the weight of the overlying layers increases under the intense gravity. This rising pressure squeezes nuclei closer together and increases the energy of the electron gas. Under such conditions, it becomes energetically favorable for electrons to be captured by protons within the nuclei, turning them into neutrons and releasing neutrinos that escape. This process makes the nuclei progressively more neutron-rich. The sequence of nuclear species present at different depths is determined by the balance between nuclear binding energies, electron capture thresholds, and pressure. Each layer of the crust at a given pressure settles into the combination of nuclei that minimizes the total energy, so the composition changes with depth in a stepwise fashion from less neutron-rich to more neutron-rich nuclei. Further down at densities much higher than those of ordinary atomic matter nuclei become so neutron-rich and the pressure so great that some neutrons are no longer bound inside nuclei at all. They leak out to form a fluid of so-called free neutrons permeating the spaces between the nuclear clusters. At this point, the crust can still be thought of as a lattice of heavy neutron-rich nuclei arranged in a regular pattern, but now this lattice is embedded not only in an electron gas, but also in a background of free neutrons. The presence of these neutrons changes the mechanical and thermal properties of the crust. They can carry mass and momentum through the lattice, interact with the nuclei through nuclear forces, and in deeper regions they are expected to form a superfluid, a state in which they flow without internal friction. Even before considering the detailed superfluid behavior, the picture in this section is that of a solid framework of nuclei whose arrangement is set by pressure and nuclear physics supported and penetrated by mobile electrons and neutrons that influence how the crust responds to stress and how it conducts heat and electricity. The crust is thin compared with the overall radius of the neutron star, occupying only a small fraction of the distance from the surface to the center, yet it plays an outsized role in many observable phenomena. Its stiffness arises from the strong electric forces between nuclei and from the high density of the lattice. The shear modulus, a measure of how resistant a material is to being distorted sideways, is many orders of magnitude larger than that of terrestrial solids. This allows the crust to support elastic deformations and to transmit shear waves, which are transverse vibrations in which layers of material slide slightly past one another while remaining bound. The frequencies of these vibrations depend on the thickness and composition of the crust and on how it is coupled to deeper layers. When the crust is disturbed, for example, by changing magnetic stresses or by adjustments in rotation, these elastic properties control how it rings and how energy is redistributed in the outer parts of the star. Because the crust sits between the dense core and the radiating surface, it also has a central role in controlling heat flow. Heat generated in the interior, whether from residual cooling from ongoing reactions or from intermittent energy release, must travel through the crust before it can escape as surface radiation. The electrons in the crust are the primary carriers of heat moving rapidly through the lattice and scattering from nuclei impurities and phonons, which are quantized vibrations of the lattice. The efficiency of this conduction is summarized by the thermal conductivity, which depends on density composition and temperature. High conductivity allows temperature differences between the interior and the surface to relax quickly, producing a fairly uniform surface temperature, while lower conductivity can maintain gradients and localized warm or cool regions for longer. Observations of neutron stars that have undergone episodes of accretion or magnetic activity and then return to quieter states show how their surface temperatures change over months and years. By comparing these changes with models of crustal cooling astrophysicists, infer the thermal conductivity and heat capacity of the crust, gaining insight into its composition and the presence of impurities. Impurities are nuclei whose charge and mass differ from the dominant species in a layer. In a perfect crystal, all lattice sites are occupied by identical nuclei, but in a real neutron star crust, nuclear reactions and accretion can produce mixtures. These impurities scatter electrons and phonons more strongly than a regular lattice does, reducing thermal and electrical conductivity. A high impurity content can therefore keep certain regions warmer or cooler for longer and can affect how quickly magnetic fields move through the crust. Over long timescales, the combination of electron transport and nuclear reactions can smooth out some compositional gradients, but in many situations the crust retains enough irregularity to leave observable imprints on cooling curves and magnetic evolution. The crust also anchors parts of the neutron star's magnetic field. In many models, currents flowing through the crust generate at least a portion of the large-scale magnetic field that threads the star and its magnetosphere. These currents are carried by the mobile electrons within the solid lattice. As the crust cools and its electrical resistivity evolves, these currents can decay or rearrange, leading to slow changes in the field. In strongly magnetized neutron stars such as magnetars, the stresses associated with tangled and evolving internal fields can load the crust with significant shear strains. Even in less extreme stars, the interplay between crustal conductivity impurities and the underlying core field influences how the overall magnetic configuration changes over millions of years. Although the detailed coupling between crust and core belongs to deeper layers than those treated fully here, it is clear at this level that the solid crust serves as both a mechanical and electromagnetic interface between the interior and the magnetosphere. Rotation also interacts with the crust in important ways. The solid lattice can support slight departures from perfect axial symmetry, such as small deformations aligned with the magnetic field or with the spin axis. These deformations, sometimes called ellipticities, are tiny in absolute terms because of the strong gravity but sufficient in principle to make the rotating star a source of continuous gravitational waves if the asymmetry is large enough and the spin rate high. Furthermore, as mentioned earlier, some explanations for sudden changes in pulsar spin called glitches invoke interactions between the crust and interior components. In those models, the superfluid neutrons in the inner crust carry angular momentum that is partially decoupled from the rigid lattice. When pinned vortices in the superfluid suddenly move or unpin, they can transfer angular momentum to the crust, causing the observed step in rotation rate. Even without specifying the detailed mechanism, it's evident that the ability of the crust to act as a rigid container that can couple to or decouple from interior flows is critical for understanding timing irregularities. In strongly magnetized neutron stars, the crust must also support magnetic stresses that act differently in different directions, because magnetic fields tend to pull along their own lines and push perpendicular to them. If these stresses build up faster than the crust can relax by slow plastic flow, they may eventually exceed the elastic limit of the solid. When that happens, the crust can crack or undergo a rapid reconfiguration of its lattice, releasing stored elastic and magnetic energy. From the viewpoint of this section, which emphasizes the existence and basic properties of the solid crust, it is enough to note that the crust's high shear strength allows such stresses to accumulate, and that its finite breaking strain sets a threshold for when more dramatic events can occur. The exact nature of those events and their connection to bursts and flares in magnetars can be considered separately, but the foundation lies in the fact that the neutron star possesses a dense, highly ordered crust capable of storing mechanical energy. Finally, the crust influences how the neutron star responds to tidal forces in binary systems. When a neutron star orbits another compact object, the gravitational pull of its companion distorts its shape slightly, raising tides on its surface and within its solid layers. The way the crust deforms and how it resists or yields to these tides affect the overall tidal deformability of the star, a quantity that can be measured indirectly through gravitational wave signals from merging binaries. A stiffer crust contributes to a particular signature in the waveforms, while a softer or partially melted crust would respond differently. In practice, the bulk of the tidal response comes from the deeper fluid layers, but the crust still contributes, especially during earlier phases of the in-spiral. Thus, the crust's elastic properties play a role not only in electromagnetic observations, but also in gravitational wave measurements. In summary, the solid crust of a neutron star is a thin but crucial layer, where nuclei arrange in a dense lattice, electrons and neutrons move through that lattice, and extreme gravity compresses everything into an exotic form of matter. This crust provides mechanical strength channels, heat, and currents, anchors magnetic fields, and mediates interactions between the interior and the surface. Although it occupies only a narrow band in radius, it has wide influence on the observable behavior of neutron stars, from their cooling and timing irregularities to their magnetic evolution and response to tidal forces, all while remaining an ordered quantum mechanical solid unlike any material found on Earth. Deeper beneath the solid outer crust at densities approaching those found in atomic nuclei, the orderly lattice of nearly spherical nuclei gradually gives way to a more complex arrangement. In this region, the pressure is so high and the spacing between nuclei so small that the competition between the attractive nuclear force and the repulsive electric force leads matter into shapes that are neither isolated nuclei nor fully uniform nuclear fluid. Instead, the nuclear component organizes into extended structures that can resemble rods, slabs, or more intricate networks, all immersed in a sea of free neutrons and electrons. Because of the variety of shapes that minimize the energy under these conditions, this regime is often described as the nuclear pasta layer, using a technical term that reflects the diversity of geometries rather than any decorative comparison. From the point of view of the neutron star, this region lies in the lower crust close to the boundary with the deeper core, and it forms a transition zone where matter loses the individuality of discrete nuclei but has not yet become a uniform mixture. In the outer crust, nuclei occupy well-separated sites in a regular lattice, and electrons move relatively freely between them. As depth increases, electron capture makes the nuclei more neutron-rich, and the pressure forces them closer together. At some point, the nuclear surfaces begin to touch and merge along preferred directions, because this arrangement reduces the total energy by sharing surfaces and optimizing the balance between nuclear attraction and electric repulsion. Calculations using nuclear models show that as density increases, the equilibrium configuration can pass through a sequence in which roughly spherical clusters give way to rod-like structures, then to slab-like layers, and eventually to configurations where the roles of high and low density regions swap with cylindrical and roughly spherical voids embedded in denser nuclear matter. These shapes are not fixed rigid objects, but continuous structures extending through the material, and their exact arrangement likely depends on temperature composition and the presence of impurities or defects. The free neutrons that permeate this region are expected to form a superfluid flowing through the spaces between the nuclear structures. The combination of nuclear clusters, superfluid neutrons and electrons yields mechanical and transport properties different from those of the simpler outer crust. The nuclear structures can carry shear stresses and define directions along which the material is stiffer or softer. The superfluid neutrons can move relative to the clusters, carrying angular momentum and heat. The electrons provide electrical and thermal conductivity, but their scattering from the intricate nuclear shapes and from any disorder influences how effectively they transport energy and currents. The result is a layer that is still solid enough to support elastic deformations but has internal degrees of freedom associated with superfluid motion and complex nuclear geometry. These features are important for understanding how stresses build and relax in the deeper crust. The nuclear pasta layer plays a key role in anchoring and transmitting magnetic and rotational stresses that arise elsewhere in the neutron star. Magnetic fields that thread the star generate forces wherever currents flow and field lines bend. In the crust, these magnetic stresses act on the lattice of nuclei, and in the pasta region they act on the extended nuclear structures. Over long timescales, slow motion of electrons and plastic flow of the nuclear material can gradually rearrange currents and fields, allowing some stress to relax. However, when the rate at which stresses are applied by processes such as the slow movement of magnetic flux anchored in deeper layers exceeds the rate at which the crust can respond smoothly, elastic strains accumulate. The nuclear pasta, with its high shear modulus and anisotropic structure, can store significant shear energy in this way. As strains grow, the material approaches a breaking threshold set by its internal cohesion and the arrangement of defects. When that threshold is reached in some region, the crust can yield suddenly. This yielding may take the form of a brittle fracture, in which cracks propagate through the lattice, or of a rapid plastic flow where the nuclear structures shift their relative positions. In either case, stored elastic energy is released on a short timescale. The disturbance propagates through the crust as waves and can couple to the magnetosphere and surface, producing observable phenomena. Events of this kind are often called star quakes, highlighting that they are global crustal adjustments in a compact star rather than local fractures in a planetary crust. The nuclear pasta layer is a natural site for such events because of its high stiffness and proximity to the core, where magnetic and rotational influences are strong. In strongly magnetized neutron stars, especially magnetas, models often attribute bursts and flares of X-rays and gamma rays to episodes in which magnetic stresses in the crust and pasta layer exceed the breaking strain. When this happens, the crust rearranges, allowing the magnetic field to change configuration. The shift in the field injects energy into the magnetosphere, accelerating particles and generating high-energy radiation. At the same time, the mechanical disturbance excites oscillations in the crust. Observations of some giant flares show quasi-periodic oscillations in the decaying tail of the emission, at frequencies that match those expected for torsional shear modes of the crust. These modes involve twisting motions in which layers of the crust, including the nuclear pasta region, oscillate relative to one another. The presence and frequencies of such oscillations provide clues about the thickness and shear properties of the crust and the stiffness of the pasta layer, although uncertainties in the magnetic field configuration and coupling to the core still limit precise inferences. Rotation introduces additional stresses in the pasta region. A rotating neutron star is slightly flattened at the equator because centrifugal forces oppose gravity more strongly there than at the poles. As the star loses rotational energy over time and spins down the equilibrium shape, it would become less oblate. However, the solid crust resists this change. The result is a misfit between the shape preferred by the current rotation rate and the shape maintained by the crust rigidity. In the outer layers, this misfit manifests as elastic strain, and in the deeper crust and pasta region, it adds to the existing magnetic and thermal stresses. When the accumulated strain exceeds the local yield threshold, a sudden adjustment can occur, allowing the star to relax to a slightly more spherical shape. Such an adjustment changes the distribution of mass within the star and therefore its moment of inertia. Because angular momentum is nearly conserved on the timescale of the event, a reduction in moment of inertia leads to a small increase in spin frequency, as observed in pulsar glitches. In this picture, the nuclear pasta layer with its strong but not infinite shear strength participates in the global event that alters the star's rotation. Other models emphasize the role of superfluid vortices in the inner crust, which pin to the nuclear lattice and then unpin, suddenly releasing stored angular momentum from the superfluid to the crust. In either case, the presence of a region where nuclei form an ordered or semi-ordered framework embedded in a superfluid is central to the dynamics. The pasta structures offer extended pinning sites and channels for superfluid flow, so the properties of this region help determine how and when angular momentum transfer can occur between interior and crust. The nuclear pasta also affects how heat moves through the inner crust. The irregular shapes of the nuclear structures and any disorder introduced by defects or compositional variations can scatter electrons more strongly than a simple lattice does. This scattering reduces thermal conductivity compared with the outer crust. If the conductivity in the pasta layer is lower, heat flowing from the core toward the surface must pass through a relatively resistive band. This can create delays and smoothing in the response of the surface temperature to changes in the interior. Observations of neutron stars that undergo periods of accretion and then return to quiescence show that some objects cool more slowly than would be expected if the entire crust were highly conductive. Models that include a nuclear pasta layer with enhanced scattering can reproduce these slower cooling curves, suggesting that the microphysics of this region leaves a macroscopic imprint on observable thermal evolution. Over longer evolutionary timescales, the electrical resistivity of the pasta layer influences how magnetic fields change. Currents that generate part of the neutron star's magnetic field may flow through the crust, including the deep layers where nuclear pasta appears. In regions of high resistivity, these currents dissipate more quickly, converting magnetic energy into heat. This process contributes to the decay of magnetic fields, especially in magnetars, and helps sustain elevated surface temperatures over tens of thousands of years. At the same time, the motion of magnetic flux through the crust is affected by its mechanical and electrical properties. In the pasta region, flux tubes and nuclear structures interact, and the interplay between nuclear and magnetic forces determines how easily the field can rearrange. Although the detailed mechanisms remain subjects of active research, it is clear at this level that the nuclear pasta layer acts as a gate through which both heat and magnetic flux must pass between core and surface, influencing the long-term magnetothermal evolution of the star. The nuclear pasta is also relevant for the response of the neutron star to external perturbations. In a binary system approaching merger, tidal forces stretch and compress the star. The deep crust, including the pasta layer, must deform in response. Its shear properties and breaking strain affect how tidal energy is stored and released, and how cracks or plastic flows might develop before the final coalescence. These deformations contribute to the tidal deformability measured through gravitational waves. If the pasta layer is very stiff, it can alter the balance of contributions from crust and core, although the bulk of the tidal response still arises from the denser inner regions. In all these contexts, the nuclear pasta region serves as a transition zone, where matter is neither a simple crystal of nuclei nor a uniform fluid, but something in between with complex geometry and rich mechanical behavior. It holds elastic stresses, hosts superfluid neutrons, scatters electrons, and interacts with magnetic flux, all under the influence of the intense gravity of the star. This combination makes it a key part of the neutron star's internal structure, controlling how the crust connects to the deeper core and how deep interior processes find expression in the observable timing thermal and high-energy activity of the star. Below the deepest layers of the crust and the nuclear pasta region, matter in a neutron star becomes more nearly uniform and enters what is called the outer core. In this region, densities are comparable to or higher than those found inside atomic nuclei, and individual nuclear clusters dissolve into a continuous fluid of strongly interacting particles. The main constituents are neutrons with a smaller but important fraction of protons, together with electrons, and at higher densities, muons, which are heavier cousins of the electron. All of these particles move in a shared dense environment, governed by the strong nuclear force and by quantum statistics. The outer core occupies most of the volume of the star between the crust and the still denser inner core, and it is here that many of the key bulk properties of the neutron star are set. The pressure that holds the star up against gravity, the way heat is stored and transported, and the way rotation and magnetic fields are transmitted through the interior all depend strongly on the physics of this region. In the outer core, neutrons and protons are packed so closely that their behavior is described not in terms of individual particles orbiting in empty space, but in terms of a quantum fluid. A quantum fluid is a state of matter in which the collective properties arise from the wave-like nature of its components, especially at low temperature. Neutron stars cool rapidly after birth, and within a relatively short time, their internal temperatures drop far below the characteristic energy scales associated with the interactions of neutrons and protons. Under these conditions, theory indicates that neutrons in the outer core form pairs joining in correlated states somewhat analogous to the way electrons pair in a conventional superconductor. When many such pairs form and share a common quantum state, the neutron component becomes a superfluid. In a superfluid, the flow of matter can occur with very low internal friction, and rotations are carried not by continuous shear, but by quantized vortices, which are tiny whirlpools each carrying a fixed amount of circulation. At the same time, protons in the outer core, though less numerous than neutrons, also pair and can form a superconducting component. A superconducting fluid is one in which electrical resistance drops to nearly zero, and magnetic fields interact with the matter in special ways, often being confined to thin tubes of flux or expelled from parts of the fluid depending on the type of superconductivity. These paired states of neutrons and protons develop as the neutron star cools and reach different depths depending on density and composition. The exact pattern of where and how strongly pairing occurs is still uncertain and depends on details of the nuclear interaction at different separations and momenta. Nevertheless, many models agree that in at least part of the outer core neutrons form a superfluid and protons a superconductor. The electrons and muons remain as highly degenerate normal fluids that carry charge and heat. The presence of superfluid and superconducting components modifies almost every aspect of the outer core's behavior. This specific heat, which measures how much energy is required to raise the temperature by a given amount, changes when particles pair because excitations across the pairing gap require extra energy. Neutrino emission processes which dominated the cooling of the young neutron star are altered as well. Some reactions are suppressed when pairing removes low-energy states, while others arise from the formation and breaking of pairs. As a result, the cooling history of the star depends sensitively on the onset and strength of superfluidity and superconductivity in the outer core. Observations of surface temperature as a function of age for several neutron stars suggest that some kind of pairing does occur in their interiors, because the inferred cooling rates are difficult to explain otherwise. The mechanical response of the outer core to rotation is also shaped by superfluidity. In a normal, fluid rotation is distributed continuously with the fluid swirling in a pattern that matches the overall angular velocity. In a neutron superfluid, rotation is carried instead by an array of quantized vortices that thread the fluid. The density of vortices is proportional to the rotation rate, so a faster spinning neutron star hosts more vortices than a slower one. As the star loses angular momentum and spins down, the superfluid must adjust by reducing the number of vortices or changing their spacing. This adjustment requires vortices to move outward through the fluid. Their motion is influenced by interactions with the surrounding matter with magnetic flux tubes in the superconducting proton component, and with structures at the boundary with the crust. If vortices pin to these structures and cannot move freely, the superfluid can temporarily maintain a higher rotation rate than the crust and charged components. When pinning eventually fails in some region, a sudden collective motion of vortices can transfer angular momentum to the crust, producing the small abrupt spin-ups observed as glitches. While other mechanisms may also contribute, the presence of a neutron superfluid in the outer core provides a natural reservoir for storing and releasing rotational energy relative to the more rigid outer layers. The proton superconductivity affects how magnetic fields are arranged and move within the outer core. In a Type II superconductor, which many models suggest is the relevant case for neutron star protons, magnetic flux penetrates the fluid in the form of thin tubes, each carrying a quantum of magnetic flux. These flux tubes form an array whose spacing is set by the average magnetic field strength. The interaction between quantized neutron vortices and proton flux tubes is a key element of many models of neutron star magneto-rotational evolution. If vortices and flux tubes are strongly coupled, the motion of one can drag the other, tying the rotation of the superfluid to the evolution of the magnetic field. If they slip past one another more easily, rotation and field can evolve more independently. The strength and character of this coupling influence how quickly the star can redistribute angular momentum internally, how magnetic fields decay or rearrange, and how stresses build at the boundaries between core and crust. The outer core also carries most of the mass of the neutron star. The relation between pressure and density in this region, known as the equation of state, determines how massive a neutron star can be for a given radius, and how compressible the matter is under gravity. Nuclear physics experiments on Earth, in which heavy ions are collided at high energies, provide partial constraints on the behavior of dense nuclear matter, but they do not reach the exact conditions found in neutron star cores. Theoretical models extend these constraints using many body calculations and effective interactions. Observationally, measurements of neutron star masses, especially of the most massive known stars, and estimates of radii from X-ray observations, place further limits on the possible equations of state. A stiffer equation of state in which pressure rises rapidly with density can support more mass against gravity and leads to larger radii for a given mass. A softer one leads to smaller radii and lower maximum masses. The fact that neutron stars with masses around 2 times the mass of the Sun exist implies that the outer core and inner core matter must provide enough pressure at high density, ruling out some very soft models. Even so, significant uncertainty remains about the detailed composition and interactions in the outer core, and multiple models are consistent with current data. Heat transport in the outer core is governed mainly by electrons, and to a lesser extent by neutrons and muons. Because the matter is so dense and the particles are strongly degenerate, small changes in their distribution can carry large amounts of energy. The thermal conductivity is generally high, allowing the inner core and outer core to remain nearly isothermal over large regions once the star has cooled beyond its earlier stages. Superfluidity can further enhance this tendency by reducing internal friction and allowing certain collective excitations to carry heat efficiently. As a result, temperature gradients within the core are often modest compared with those between core and crust. This relatively uniform core temperature sets a baseline for the thermal evolution of the entire star, with the crust and envelope controlling how heat leaks out to the surface. The outer core responds to tidal forces and oscillations as a fluid body. When the star vibrates or is distorted by a companion's gravity, the superfluid neutrons and superconducting protons move in coupled ways. The fluid supports various modes of oscillation, including density waves shear like relative motions between different components, and global pressure modes. Some of these modes can be excited during starquakes, magnetar flares, or binary interactions, and they can radiate energy in the form of gravitational waves or damp into heat. The frequencies and damping times of these modes depend on the equation of state, on the strength and distribution of superfluidity and superconductivity, and on how the core is coupled to the crust. While many details remain uncertain, it is clear that the outer core is not a static interior, but a dynamic quantum fluid whose properties control how the neutron star rings and relaxes after disturbances. At the boundary between the outer core and the inner core density and pressure reach values where more exotic forms of matter may appear. The exact location of this boundary and the nature of the matter beyond it are not yet firmly established, and they belong to more uncertain regions of neutron star physics. From the perspective of this section, it is sufficient to note that the outer core provides a relatively better constrained layer, in which matter is dominated by neutrons with a smaller fraction of protons, electrons and muons, and in which superfluid and superconducting phases are expected to exist over a substantial depth range. This layer sets much of the star's response to cooling rotation and magnetism, and anchors the more speculative physics of the inner core to the better understood behavior of dense nuclear matter just above the nuclear saturation density. In this way, the outer core forms the main body of the neutron star, bridging the structured crust and nuclear pasta above, with the still more compact and uncertain inner core below, while embodying the quantum fluid nature of matter under extreme pressure and gravity. At the very center of a neutron star, beneath the outer core where neutrons and protons form a quantum fluid, lies the inner core, a region where densities and pressures reach their highest values and where the nature of matter is least certain. In this central zone, the density is expected to be several times higher than the density inside atomic nuclei, and gravity compresses matter into a state that cannot be reproduced directly in terrestrial experiments. The material here is still made of the same basic building blocks that appear elsewhere in nuclear physics, but the way these building blocks arrange and interact is unknown in detail. What is reasonably well established is that the inner core must provide enough pressure to support neutron stars with masses around or above twice the mass of the Sun without collapsing further into black holes, and that it must connect smoothly to the outer core at somewhat lower density. Within these broad constraints, many models of inner core matter remain possible, and the inner core stands as the deepest layer where the structure of the star is controlled by physics that is only partially understood. In the simplest and most conservative descriptions, the inner core is an extension of the outer core composition still dominated by neutrons, with a smaller fraction of protons, electrons and muons, but with all components pushed to higher densities and Fermi energies. In such models, the transition from outer to inner core is gradual with no sharp phase change, and the equation of state remains a continuous function of density. Neutrons and protons continue to form superfluid and superconducting pairs, perhaps in different pairing channels than in the outer core because the balance between nuclear attraction and repulsion shifts at higher densities. The properties of the superfluid and superconducting phases, such as the size of the pairing gaps and the range of densities over which they exist, affect the specific heat and neutrino emission rates in the inner core just as in the outer core, but quantitative details are uncertain because the nuclear interaction in this regime is not fully constrained. Even within this conservative picture, different theoretical treatments predict different stiffness for the equation of state, leading to different inner core sizes and pressure profiles. Beyond these scenarios, many models allow or even favour the appearance of additional particle species in the inner core. At very high densities, it can become energetically favourable for some neutrons to transform into particles called hyperons, which are baryons containing strange quarks as well as up and down quarks. Candidates include particles such as the lambda and sigma hyperons. Their appearance would introduce new degrees of freedom into the fluid, allowing the system to lower its energy by distributing baryon number among several species. However, because hyperons add states in which baryons can reside, their presence tends to soften the equation of state, meaning that pressure rises less quickly with density. If this softening is too strong, it becomes difficult for the inner core to support very massive neutron stars. To avoid this problem, models that include hyperons often require additional repulsive interactions at high density to maintain sufficient pressure. The strength and nature of these interactions are not yet well determined, so the hyperon content of the inner core remains an open question. Other proposed components in the inner core include meson condensates. Mesons are particles made of a quark and an antiquark, such as pions and kaons. Under some conditions, theory suggests that a macroscopic population of mesons can occupy the same quantum state, forming a condensate. A pion or kaon condensate in neutron star matter would change the composition and soften the equation of state in ways similar to or greater than hyperons, again raising concerns about the maximum mass that could be supported. Such condensates would also alter neutrino emission processes, potentially enhancing cooling rates. Whether these condensates actually form in neutron star inner cores depends on the detailed balance of chemical potentials, densities and interactions at high density. Current observational constraints on masses and radii disfavour some of the softest equations of state associated with strong condensate formation, but do not yet rule out all possibilities. A more radical possibility is that the inner core contains deconfined quark matter. In normal nuclear matter, quarks are confined inside baryons such as neutrons and protons. At sufficiently high density, some models of quantum chromodynamics, the theory of strong interactions, predict that quark confinement may be lost, and matter could consist of up-down, and possibly strange quarks moving more freely in a uniform background. This deconfined quark matter might appear in a central region surrounded by a shell of hadronic matter, or there might be a mixed phase where quark matter and hadronic matter coexist in complex geometries. Within quark matter, quarks themselves are expected to pair in analogy to superconductivity forming phases that are often called color superconducting states. Different patterns of pairing, such as pairing between different flavors or colors of quarks, lead to different microphysical properties. As with hyperons and meson condensates, the presence of quark matter affects the equation of state sometimes softening it and sometimes stiffening it depending on how interactions are treated. Inner cores with quark matter must still produce neutron stars with observed high masses, so only some subsets of these models remain viable. At present, it is not known whether any neutron stars actually contain deconfined quark matter inside, so the inner core is a region where the possible presence of this phase remains a leading but unconfirmed idea. Regardless of the exact composition, the inner core plays a central role in setting global neutron star properties that can be measured. The relation between mass and radius is sensitive to how much pressure the inner core provides at a given density. Very massive neutron stars are particularly informative because their central densities probe parts of the equation of state that lower mass stars do not reach. The existence of neutron stars with masses around twice that of the Sun sets a firm requirement that the combined outer and inner core matter must be sufficiently stiff at high density. Observations of radii through modelling of X-ray emission and of tidal deformability through gravitational waves from binary mergers add complementary constraints. The tidal deformability, which describes how easily a star's shape distorts under an external gravitational field, depends strongly on the star's compactness and therefore on its internal pressure profile. Analyses of gravitational wave signals from merging neutron stars indicate that matter at several times nuclear density cannot be too soft without conflicting with the observed deformabilities. Together, these constraints carve out a region of allowed equations of state in which inner core matter must lie, but they do not yet uniquely determine its composition. The inner core also affects dynamical behavior when neutron stars interact in binaries or undergo rapid internal changes. During the coalescence of two neutron stars, the inner cores are compressed and heated, possibly driving matter into regimes that differ from those in isolated stars. The gravitational wave signal from the merger and the electromagnetic emission from any ejector carry information about the equation of state at these extreme conditions. If a phase transition occurs in the inner core at some critical density, it could in principle leave signatures such as characteristic frequencies in the post-merger gravitational wave signal or distinctive features in the mass distribution of neutron stars that reflect a sudden change in internal structure beyond some threshold mass. Current observations are not yet precise enough to confirm such features, but future detections with improved sensitivity may probe these possibilities more deeply. Cooling behavior also depends on inner core physics. Neutrino emission processes in the inner core can be more efficient than in the outer core if new channels open, due to the presence of hyperons, meson condensates, or quark matter. In some models, rapid cooling via direct neutrino emission processes is allowed only above certain densities, leading to different cooling tracks for neutron stars of different masses. Heavier stars with inner cores above the threshold might cool faster than lighter ones that lack such cores. Observational hints of unusually rapid cooling in some young neutron stars have motivated studies of these enhanced emission mechanisms. At the same time, superfluid and superconducting gaps in the inner core suppress some reactions and introduce neutrino emission from pair breaking and formation. The combined effects of these processes produce a range of possible cooling histories, and matching observed temperatures and ages requires careful tuning of inner core parameters. Although this tuning does not yet yield a unique solution, it provides another window on the physics of the deepest layers. The presence of superfluidity and superconductivity in the inner core also affects how rotation and magnetic fields evolve. If the inner core contains superfluid neutrons and superconducting protons, it will host quantized vortices and flux tubes, as in the outer core but under even higher densities and perhaps different pairing patterns. The way these structures pin, move and interact in the inner core contributes to the global redistribution of angular momentum and magnetic flux, especially over long timescales. If quark matter is present and color superconducting magnetic fields may penetrate in the form of color, magnetic flux tubes and rotational vortices may have different properties than in hadronic matter. These possibilities remain theoretical, but they illustrate how the deepest composition influences macroscopic behavior that might reach the surface through timing, irregularities, magnetic evolution, or responses to tidal forces. The inner core therefore stands at the intersection of microphysics and global observables, even though the details of that intersection are not yet fully traced. Experimental and theoretical nuclear physics provide partial guidance. Studies of dense matter in heavy ion collisions, measurements of the symmetry energy that characterizes how nuclear energy depends on the imbalance between neutrons and protons, and advances in quantum chromodynamics. Calculations all constrain aspects of the equation of state. However, laboratory experiments reach densities and timescales that differ from those in neutron star cores, and calculations become more challenging as density increases and many body effects grow. As a result, there remains a gap between what can be computed or measured directly and what is needed to describe inner core matter in full detail. Neutron stars therefore act as natural laboratories that complement terrestrial work. By combining astronomical data on masses, radii cooling and gravitational waves with nuclear theory researchers gradually narrow the range of acceptable inner core models, but a definitive identification of the state of matter at the center has not yet been achieved. From the structural point of view, the inner core is the final region reached, when moving inward from the galactic context progenitor, evolution, and supernova birth through magnetosphere, surface crust, and outer core. It is the densest part of the neutron star where matter reaches its most compact form while still resisting collapse. It provides the central pressure that supports the star set's part of the relation between mass and radius, and influences how the star responds to cooling, rotation, and deformation. At the same time, it is the region where theoretical uncertainty is greatest because the physics of strongly interacting matter at such densities admits several plausible scenarios that are consistent with current observations. In this sense, the inner core encapsulates both the progress made in understanding neutron stars and the remaining open questions about matter under extreme compression, completing the inward journey through the layered structure of these compact remnants, while leaving room for further refinement as new data and theories emerge.